Good. Mm.
Sorry, Professor Kai, should we wait or should we kickstart it?
We will wait for 1 minute, sir.
Okay, that's okay. Fine. There's a bit of a radio silence, so just wondering. Although I could see you.
It's a sharp 6.01. Good evening to all of you. Today is a second day of our FDP. First of all, on behalf of management principal of Shivnagar Vidya Prasarak Mandals College of Engineering, I welcome today's resource person, Mr.Swapnil Kulkarni from United Kingdom. Let me briefly, first of all, introduce him. Mr. Swapnil Kulkarni completed his MTech in the year 2014 from COAP Technological University. His seasoned and experienced electronics engineer with 18 years of experience in working with various government project, defense contractors, OEM across globe for electronic warfare solutions. His expertise in technical management, implementing customized spectrum engineering solutions via customization and coding with background of computational electromagnetics, as well as his expertise on EV powertrain, cable harness design, optimization, PCB design, in the chip VLSI design, circuit design and simulation. He has hands-on design, development, testing and delivery of radar system, ECM. He has expertise on anti-jamming solutions, guided weapon system, infrared seekers, underwater communication, SATCOM for various Tier 1, Tier 2 suppliers. He has patent work on ultrasonic motors and battery management system for ultra low power devices. He has expertise on algorithms for virtual flight validation of WinPro, deliver on-site projects for top 4 automotive companies. He also established the vehicle connectivity and ADAS solutions, expertise on ADAS solution, signal processing for communication, blocks, and filters. So these are the expertise area. So I warmly welcome today's resource person, Mr. Swapnil Kulkarni from United Kingdom once again. And over to you, sir.
Can you hear me now?
Yes, sir.
Yeah, my apologies. I was on mute. Sorry. So first of all, I would like to thank you very much, Professor Kai, Principal Sir, and all of the management for inviting me to this session. It's my privilege. It's worth to mention that I'm ex-alumni of SVMPS, so probably I'm 2006 pass out. And if I recall, I did my specialization, that was VLSI, and Doshi madam, she should be still around, I believe. And there were a couple of other professors, I'm not sure they are there or might have moved. But yes, I could see one familiar name, my friend and colleague, which we studied together. I will address him with first name, but Javed, here I am. And also, thanks for reaching me out. Again, I'm very privileged to present this session. What I'm going to plan is my topic is more on probably satellite communication and networks. So I'll try to cover some brief idea and what are the different engineering aspects. I come from a very core engineering background. So I did some coding in the start of my career, but that didn't fascinated me much, and I was always wanted to spend my share interest was more in the engineering side. So allow me to share my screen. Okay, should be okay. We'll have. Can you see my screen?
Yes, sir. Yes, sir. It's fine.
Okay, so for my specs. So my topic here is, of course, I work for a company called Engineering. I'm just going to use call me lazy. You should. It's free to tag me that. I'm just using my default template. But the idea here, whole and soul, is about space communication and satellite networks. Now, there are various tools in the industries which are free to explore and use, even available for the academics. I use some of the preferred tools, but that said, it's not necessary you should stick to those one. The main idea behind is to understand the workflow on the engineering aspect from end-to-end solution. When you talk about space communication and satellite, things probably don't appear as simple as a satellite box. I would say there's more aspects. It comes from the structural, CFD, your communication, and other stuff. So the very first aspect I would say when you talk about communication, and being my background, I did my wide wireless is primarily the antennas which are used to communicate. If you look at the satellite, there are various aspects. First of all, your transmit TXRX transmitter receivers or tier trans receivers. Secondly, and the most important aspects is your power module, which is battery. Third but not least is the inverters or power converters. Then comes something on your electronic system design or your microcontroller and motherboard, which is PCBs. And then last but not least, I would say is the how does the SATCOM really operates, or in real world, have you ever imagined if you run a call, or probably we do a lot of VoIP nowadays, more day-to-day life example would be you do a lot of WhatsApp calling, okay? But the call is always rerouted through your nearest cellular operator up to the satellite. And bear in mind the fact the relay of signal doesn't occur straightway, it's never line of sight. When it moves through various layers within your atmospheric system or even within the MAC layer, physical layer, and I'm not touching in the very intrinsic detail, but it has to, at a certain point, the signal has to be relayed from one satellite to another satellite and down to the Earth control station. Everything occurs at the back end within probably milliseconds, and you won't even realize the delay. However, there are a lot of aspects to the SATCOM or satellite communication. The first and very primary, what you observe physically with your bare naked eyes, and it says that probably the best way to learn is to observe. And probably, if I'm right, what I read a long years ago, I was a avid reader. Now that I'm not, probably due to the work what I deal with, but most of the time your brain will absorb what it sees. 80% of your, I would say, understanding analysis through your perception or what you look at. So if you look at a satellite, obviously the first thing comes in your picture would be a solar panels, but there'll be a lot of protruding structure, essentially antennas, and there'll be some bits and bobs spread all across. Now there are different kind of antennas, a potential area to export. I'm not saying it is saturated. There are a lot of new innovations coming in. Probably FSS metamaterial is saturated. What you can look here is, and what I want to touch base, where exactly the industry is moving. You might have heard these fancy terms. I don't want to bog you down. So being mindful of time because I have to cover 4 different topics. These are more realistic antennas, I would say, right from your reflectors. Bear in mind the fact even today most of the satellite communication they use heavily reliant on waveguide, and because you inherently have to pump high amount of power down to earth and vice versa when it's received in order to amplify. Of course, patch antennas are definitely used, but they have very limited and restricted usage, and they are preferred only in a certain frequency bands. So when you might have heard these terms payload and other stuff, but inherently the satellite is designed for a certain payload. Payload is a very generic term. Don't mess up with the actual weight. It essentially caters to what bandwidth is gonna cater with what frequency. So you might have heard that some of those are geo, LEO, or geosynchronous satellites, etc. However, each of them will cater a specific band: S band, C band, KU band, or different KU band may not be used. My apologies, but VHF, UHF, yes, they are used, and then X band is very common. So based on the payload of the bandwidth and the frequency is going to cater, and is it purely for a civilian approach or surveillance or military? Yes, your different kind of antennas will be used, but by far and large, this is a fact that at least in SATCOM and even the receiver side, you'll still find conventional antennas. Of course, there's lot of innovative engineering has been deployed, and there are different numerical solvers which are used to design, simulate. You of course have to move at the end of the day to fabrication. That's a different aspects. I'm not covering the fabrication part because I have a very little experience in. I have done in the earlier days a lot of designing and fabricating the actual antennas, but now that I have lost a bit of touch, so being very transparent and honest. Based on your class and type of antenna, you will need to switch to different numerical solvers. It's a very known established fact in any engineering aspect. If you are dealing with mechanical or civil, even in civil engineering, there are a lot of simulation tools used nowadays, or inherently it was the electronics, and I would say, yes, the electronics and electromagnetic domain which has pushed a lot of simulation tool. Someone argue yes, some will definitely argue that is the CFD and the structural side, but yes, finite element method is a pretty old solver, but inherently it is an, I would say, a hierarchy carried from structural side. FEM in electromagnetics or antennas purely is used to handle inhomogeneous or different kind of materials or dielectrics. That said, you are free to use any tool, but bear in mind the fact based on the electrical size, what gain you are looking at, what bandwidth, and what is it looking at, is it going to cater a multi-band or kind of payload or just specific frequencies, you will need to switch to specific class and type and size of antennas, and then you'll require different numerical solver. This may be an abbreviation. You can search later. You can use a time domain code or method of moments or frequency domain code. MOM stands for method of moment. I'm not going to detail abbreviation in the interest of time. Okay, just going to skip this. Let's move to the more realistic term. This is a known fact that if you design something, it's very rare unless you are a very good designer or a very good engineer, your specifications are going to match the exact end requirements. So you will have to have optimize it. You need to work out with certain design variables and then see, okay, how these things are gonna fit into the real world requirement. Now that said, let's take a classic example of a basic element of a satellite, which is an antenna. It doesn't matter what it is. Are you looking at a patch, or is it an array, or is it a simple dipole or a monopole? That doesn't matter. What you typically do when you design a system, let's say even if it's a rectifier or it's a power converter or whatever, the reason I will cover, I'm going off topic a bit, is very few people are aware that in satellite power management is very critical. And if you are aware, most of us are, that everything runs on batteries. But have you ever thought the battery, the critical, I would say it's the I won't say brain, but the neural network of satellite is the inverter circuit. Essentially, the batteries or the solar arrays, they will harness the solar, it's known fact, and then it charges the battery, and the battery then powers the whole of the system. The key fact is the battery is standardized at a certain voltage, depends, 48 volt or 24. However, none of your these digital or analog circuits or the other devices on the satellite operate at 48 volt. You need a power converter. A power converter is a brain of any electronic instrument. For example, let's take off your simple handset. Okay, now you need to charge this. You probably plug into your AC mains, and it has a small power converter. So you always need an AC to DC converter or a DC to DC converter, because even take a classic example of your automotive battery, which is typically 12 volt, 48 volt depend. However, all of the other subsystem work at 5 volt, 12 volt, 16 volt. So you'll need a converter, which is the most crucial part of any satellite design. And it has to be very robust, stable. It should give a condition DC supply. So that's where the power converter comes into picture. Rolling back. So the way you design is you have your initial design, you look what are the performances, how does my gain looks, what is my VSWR. The second aspects would be, okay, if you're not happy or you want to tune, you modify the design and look. However, this is more of a manual process. What I'm gonna show is, yes, before I skip something, show the more, I don't want to throw those fancy terms, rather show some more realistic example. You might be aware about all of this. Probably it's been more than 2 or 3 years. Everyone is talking. If you open LinkedIn, literally any Tom, Dick, Harry just throws these jargons, AI, machine learning, and data. However, if you really look into the actual implementation, there are very few realistic examples. What I want to show in the next work slides or probably is how can you work with real world, essentially just the math model or math algorithms you use to optimize your designs, more fancily which are termed as AI and machine learning, but that's not the case. I would definitely highlight one of the project which I did in masters is it's one of the, if you ever Google you could figure out. So Pico satellite and use our own code. I have done some coding long years ago, probably most of 2 decades ago. Some computational coding I have done for the same code. So I work for Altair. I'm not propagating that. Said you can use any tool available to you, any of it, be it MATLAB or open source, is absolutely your call. But we use in this case FICO to specifically design the antennas, and was very happy. The satellite did die because it has a very limited span. It's a Pico satellite. Then bear in mind the fact this is a new trend. I thought it's important to just highlight space-based solar power. A lot of countries across the globe are, or the governments are pumping these funds. Essentially, you harness the solar energy in the space, and then you divert that energy into high power micro beams, which can be then received on the Earth station, and then that power can be pumped back into the grid. But that is a quite complex engineering problem. I'm not gonna touch this. Another interesting application I've seen is instead of conventional, you might be aware about. I will touch base on the optimization stuff, but just a couple of things where the technology is moving. Um, if you might have heard about this when the satellite is launched in the orbit, obviously it always drifts, and then you have to fire some thrusters to bring it in the right orbit so that it looks at the right, or it is looking at the right receiver station on the Earth, or it's covering specific areas. The very classical way is you have liquid oxygen propulsion jets, but this is a way innovative. I think a couple of satellites have already started harvesting. I don't name who and what because of the NDAs, but what you are observing is essentially this is a high power micro antenna. What it does is it ionizes the plasma and uses as a thrust. It vectorizes this plasma through an, essentially it's a waveguide cavity antenna but a high power. It ionizes your plasma and uses that plasma in the direction to thrust or to propel or change the direction of your satellite. So it's quite innovative because for very reason you don't need to carry any liquid or solid propellant on the top. It's energy efficient. So let's move on. I'm in the interest of time just gonna escape something and jump directly to an example. There are a lot of stuff jargons, but I'm just straight away put on to the machine learning, specifically in the electronics and electromagnetic domain. Okay. Now, obviously, you might have heard this term here and there, but the question really is what? Sorry, any noise or questions? My apologies. Is it just me, or is anyone hearing any background noise? Okay, that's look fine now. So let's rather, instead of making complex terms and throwing those jargons, I would prefer to work with a simple example to understand what exactly machine learning means in context with any of the. I don't want to use the regression model and everything. Give me a couple of seconds. I'm just going to skip this. Yes. Let's take an example of a very simple basic antenna. Doesn't matter at what frequency it is. Again, patch antenna because people nowadays fancy a lot. But to me, believe me, in the real world, patch antennas have very restricted bandwidth and limited usage. Not that they are, of course, if you are looking at low power and medium range devices, you will find them everywhere. Rolling back. Let us say you have designed an antenna. I'll also come later to a circuit, and it has some XYZ performance. So when you design something, obviously you have a design variables. When we talk about design variables, they could be anything. It could be the physical dimension of the structure or electrical parameters. So it could be anything. For example, if you're just designing a Colpit oscillator, you are looking at what are my resistors and capacitors values, or what is my required output, what is my sample, how I'm looking at the square wave, what is the sampling rate, and etc. Similarly, in case of this antenna, there are some design variable, which is the physical dimension, as well as the electrical or electronic parameters. It could be like, what is my transmit power, how much amount of, let's say this antenna is radiating 30 watt of power, for the sake of argument. Rolling back, in this case, this design has a couple of design variables, which is the patch size. When I say patch size, it could be like, what is the length of my patch, width of my patch, where exactly is the feed position. In real world, most of the antennas are coaxial feed. That's the different. It could be feed through a classic coaxial feed, or can use an SMA or BM, whatever connectors. That's not the point here. What you're looking is the dimensions of the antenna, which could be the length and width, or the length and width of the slot, length and width of this antenna, and what is the slot to patch distance. Okay. Now what you do is essentially when you do an optimization, essentially you can use different tools. We have something like HyperStudy, but you can find out any tool, which is what it does is multivariable, multi-parameter optimization engine. This is what the industry looks at or is in practice. What we want to look is, out of all of my design variable, which of these design variable have maximum impact on my design. So in this case, what you do is you prepare your CAD model of the antenna, and then you give it to a HyperStudy, whatever. It's just, you just say, please do a design of experiment. TO is nothing but you launch multiple simulation, or you can do multiple calculation by hand or by MATLAB, either way, or use a simulation tool. It's entirely your call. And what it does, it with a number of calculations or simulation or your own MATLAB code iteration, it essentially does a wide variety of combination of values of this design variable, be it patch slot length, slot width, or patch dimension, or feed location. So you can imagine if you have just two design variable, you have a matrix of 2 by 2, which would be 4 simulations or 4, I would say, hand calculation, or 4 whatever your MATLAB or whatever code you want to use. Okay. Now imagine if you have 5 design variable, your matrix should be then at least 5 by 5, isn't it? So you will have at least 25 designs of patch antenna, wherein you will have different dimension of patch size, slot width, slot length, etc. What the optimization engine does, it tells you, okay, look, out of all of these 5 design variables, there are only 2 design variables which have maximum impact on my S11 or return loss. The other design variable have least impact, just ignore. So how does it helps you from the machine learning point of view? That is the key aspect here, what I want to explain. What the machine learning algorithm does it, of course, you can define that. Now, I don't want to consider all of the design variables, but rather what it tells is, now again, there are a lot of algorithms available, and I would happy to say it was our technology which was first in across the industry who have pushed in machine learning specifically for the electromagnetic side of application. When you talk about electronics and electromagnetic, it's a quite broad spectrum. I'm talking more focused towards a radiating and scattering problem. So MELS is one of the proven algorithm, and what it does, it essentially it trains your simulation data or your hand calculation data or historical data or even measurement data. Let's say you can argue that, oh, we already have an existing antenna system or a transceiver, and this is how it has performed. You can come back, get the measure data, feed into the optimization engine, and what it does, it will train. Let's keep it simple. It will train the simulation data and generate a math model, and that is what the fancy term machine learning, but essentially it's a simple math model or a mathematical equation. The mathematical equation is prepared based on the extraction of data from your simulation model or your hand calculation model or MATLAB or whatever you use. And what it does, it generates a response surface from your machine learning model. Essentially, it will generate a response surface and show you, okay, if I change the feed position, say from 18 mm to 25 mm, if I change the slot length from say 42, say approximately 40 mm to 44 mm, if slot width from 1 mm to say 6 mm, how would my S parameter look? And then it will give an idea that probably just by moving the slider instead of doing, because now it has generated a math model based on your number of simulation models. It's very easy merely by moving this slider to identify what optimum value you'll get the best S parameter. The key aspect to remember here is machine learning or data science it is not a magic. It is purely a mathematical approach. Remember, it takes time to solve say 25 models with different dimensions of your designs. In this case, it's a simple patch antenna. So obviously you spend finite amount of time to solve those models and then extract the data from those solved models. So you might feel that it's magic, but it's not magic. If you do a conventional optimization, you could see it will take probably 810 seconds because it's a very simple patch antenna, and believe it, this is on infinite ground plane. None of your real world structures are on infinite ground plane. Unfortunately, the textual, what I learned and even probably has changed. All of the example, they talk very nice, beautiful responses and curve. they are mostly on infinite ground plane. That is the never case. All of your real world antenna will have a finite ground plane, and it's very important to consider when you design or solve about this aspect. Okay. Now remember what I mentioned is the machine learning model or the math model is generated based on the number of simulation model or your MATLAB models or hand calculation model you have done that takes finite time. So in order to collect that data or extract that data and then build a math model, which then you can use for direct optimization, which might look magic 4 seconds, but that is not the case. Total time you spend here is then 162 plus 4 plus 6, essentially 168 seconds. Yes, you do save time, but bear in mind the fact that it's not a magic machine learning or data science, what you call. That's data science I haven't touched because that's a different aspect. I hope that's clear. So more importantly, it is key to understand is remember sometimes the the math model which is generated based on your data extracted from your n number of simulation models, it may not be sufficient. So if it might happen that, so what I'm showing you is this is a regular optimization. This is the nice S11 at say close to minus 21, 22 dB. This is the S11 obtained through machine learning, and this is how the unoptimized look. You might question, the argument is very valid that this is not exactly matching for very obvious reason, because if you oversample, say for now, this model I have just generated 25 simulation model, or you can say 25 hand calculation model, or 25 MATLAB, or whatever code you use. I'm not promoting MATLAB. Probably I won't, because there are a lot of open source code and they are quite good. So the argument is here, if you go instead of 25, instead of solving this model 25 times by changing the different dimensions or electrical parameters, you can solve 50 models, and then this curve will be more closer. The question is how much time you want to spend for generating the data or extracting the data, and that's where what the industry prefer, or we use HyperStudy. It will identify what exact number of sample data or how many simulation runs or design iteration you need to consider. So that is there's still an undebatable question whenever you talk to any machine learning. I'm going to stop here in the interest of time, but that's what I wanted to cover. How does multivariable, multi-parameter optimization is used in order to achieve real world stuff. What I'm going to do is now minimize this and move on to the next topic in the interest of time. Bear with me for a couple of seconds, which is critical because I have to cover that, and I'll then, in the interest of time, will cover some other stuff. Here I am. Yes. So the other aspect is, before I move to the satellite connectivity, is how does satellite communication work? I mean, one would argue, well, the signal is relayed from your any base station antenna up to the satellite, and then maybe if it's within the range or within the coverage area, or what we call footprint or power flux density, if it's within that threshold, the signal will be directly transmitted. If not, it will be relayed to the second satellite and then down to the Earth surface. Unfortunately, things are not that easy. So there are different tools available which can be used to define satellite networks, but you need to inherently, first of all, understand how the propagation occurs within the space. Your signal gets attenuated at different level based on what frequency you are using and what kind of satellite network are you dealing with. Is it a LEO, MEO, or a GEO, or GNSS? Then you are talking about 36,000 kilometers away. That's a different story. But in general, the way the signal is relayed is from Earth surface, say point A, I've just used a point A, any location A or XYZ, up to space and down to your receiver station. There could be a case wherein more than one satellite is involved because it's a long distance communication, let's say transatlantic, or it's very common. You have a lot of people these days traveling here and there. But if you need someone initiate a call from where I did migration, so SVPM, and up somewhere in Germany or down, obviously it's not a single point to point. Your signal will be relayed through at least one satellite network to other. Okay. So what are the aspects you need to consider in satellite radio coverage? First of all is, obviously the first aspect is the satellite has to consider some ground coverage calculation of what is your free space loss, what is the attenuation due to atmospheric gases. So there are certain ITU standards which are to be considered here. Then that is very obvious. However, if you ask from a satellite design point of view or a payload engineer, he would prefer that my beam is very sharp pointed and it just reaches to the exact receiver station on the earth, but that never occurs in your real world. So your beam is bound to spread due to different aspects. So imagine it's a very basic theory of a raylight. I recall it was when I did the, what was that, microwave engineering. I can't recall. So black thick book. Ironically, the author was probably saying what I have the surname. That's just a namesake coincidence, but there was a specific chapter on the really scattering, okay, or essentially what I can't recall is optics. There are basic principle: scattering, reflection, diffraction, and okay, so those aspects. So your beam is bound to spread. Uh, People might argue, what nowadays there's also about talk about laser beam used for communication, but even they are not prone. They as well swim. If you have gone to any parties or not, I'm not going again off the topic, but you might have seen those laser shows. So they are not very high quality. I would say laser is more for infotainment system. But if you observe, the laser does spread, the beam does spread. That's the easiest way I can explain. Here we are talking about the communication beam or the beam spreading of your electromagnetic signal, which is bound to happen. Again, this is a very important aspect you need to consider if you are dealing with satellite networks is amplitude scintillation. That is what it means essentially is obviously due to delays as well as the how would I say, the phase changes of the signal when it's propagated up from the satellite. I'm saying it the most explain the most simplest way down to the Earth surface. There are some how would I say, noises added into the amplitude of signal. Probably we all have learned, or you might have gone through in the graduation uh, course, I believe, the syllabus. There is a concept modulation and demodulation. So obviously, when I'm talking, it's an analog signal, and then when you interpret, it's an analog signal. That's an interesting case. A lot of people talk about digital communication, digital signal processing, blah 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 stuff. The irony is, if you look carefully and observe carefully, everything in the real world is analog. Okay, I'm speaking that's analog signal which travels over a VoIP. It's encoded and then decoded. These are basic communication blocks: encoding, decoding, modulation, demodulation. So modulation is not, I would say, main culprit, but demodulation definitely contributes to amplitude scintillation. Because obviously in demodulation, there are, imagine in simplest way, the receiver might use different hardware. It may have a certain tolerance and accuracy and stuff. So obviously that's bound to happen. But bear in mind the fact all of the communication aspects is everything's analog. For example, if you take a image is by defined theory is an analog. That's a different aspect. It is pixelized, it gets digitized, and when you transmit, you have a lot of options these days. You want to make it as a HD or a low resolution, or you can change it in sync, and then it goes through a medium, wired or wireless, and it's at the other end it is received, and you again decode or deconstruct, etc. I'm not even touching about the image processing algorithm used in satellite. That's a different aspect. Rolling back, in satellite or networks, another aspect is time dynamic analysis. The most important aspect is in all of the satcom, remember everything is time variant. So although I'm communicating, so I'm in a different time zone, probably you are sitting in a different time zone. However, this is still time dynamic or time variant aspect is very critical in satellite. I will explain with probably a simple video what I mean here. Again, another aspect is to consider the noise in all the receivers. Remember, there is interference within the satellite networks, also interference between the space services and terrestrial services. There could be wanted or unwanted interferences within the space. You might have heard these terms a lot, like jamming. It's very common, and it's not an alien concept. Now, probably you might have watched those James Bond kind of movie or any sci-fi movies, but this is not alien concept. You can actually jam a certain channel of a satellite in itself. Forget about jamming a specific signal on a specific building level. That is, I would say, almost a decade old technology that is already established. So remember, another aspect while considering or designing the satellite networks is how are you going to tackle the noise and interference. It could be unwanted or wanted. So when it comes to noise, essentially you might have heard this term SNIR ratio, signal to noise. It may sound dumb when we do a theory, but in real world, SNIR and adjacent channel recurrence ratio, they play a very critical role while defining the receiver characteristics. Third but not least is when your satellite is gonna transmit and something is getting received on your Earth station, there are a lot of more propagation aspects in real world. Your signal or your beam will be affected a lot due to blocking, due to buildings, terrain profile, or foliage, essential vegetation, or even the atmospheric composition. So you might have seen those images here and there, lying like how does APAC or the Asia Pacific region or certain cities in Asia Pacific look during night time. You might see heavy industrial activities and a lot of illumination, but believe me, those images, the way they are generated, you require a lot of filtering because your atmosphere is essentially polluted by a lot of dust particulate and pollutants. And when you transmit or when you capture an image, but when you want to transmit, it gets your beam gets scattered, and how would I say? There's a lot of noise added on the modulation aspect. So yes, you will have to have consider how the signal is. You want to ideally have a zero blockage, but that's not possible in the real world. Secondly is how many number of satellites are visible. Look from the other perspective now. This all for long I have been talking about how the satellite is gonna send the signal down to Earth. What about from the receiver side or the Earth station side? You will need to always mindful how many number of satellites are visible, what is the received power per satellite, which is more technical than power flux density. There will be always multipath errors. Remember, if when you transmit a signal and when it is relayed down to at whatever desired location be on your Earth surface, it's not by through just single path. It is sent to multiple path and down is and then coagulate. I would say not coagulated, but uh, again rolling back to the multiplexing, made into multiplexing and demultiplexing. That's what occurs in your real world communication channel. So multipath errors, they are again bound to happen. How are you going to tackle that? There's a lot of I would say focus on the industry on how to tackle multipath errors and how to reduce the noise. So those could be another topics. Another aspect is people clearly ignore, but look angles is very critical in satcom. Is essentially look angle is the angle, literally it's the angle between your what the satellite looks down to the ground. So if it decreases, then obviously your distance between transmitter and receiver is gonna increase, and that essentially your path loss will increase, which is very clear. You want the least amount of path loss. Path loss, I hope you are familiar with this term, but it goes by literally name. So literally, let's be, how would I make it more simple? With acoustic example, yeah. So when you speak, okay, however high a human voice has a limitation. So I can speak with a certain magnitude. I can raise my volume. I can go to the peak beyond which I can't shout louder. So what the reason I'm explaining this is my voice would then travel maybe 200 meters at the max, 400 meters, and after that it will cease, it will die out. So same is what occurs with your real world wireless signals or your electromagnetic signal. There is a path loss associated. So your signal may reach say beyond certain kilometers, but if it is below noise floor or noise threshold, it is just noise. So if let's say your received signal strength is less than minus 90 dB, it's just noise. You can't demodulate or you can't decode back what is the original information. It's just lost then. Another aspect is the distance between satellite and Earth station. If it increases, obviously, so it's a very logical your path loss is going to increase. What if your angle decreases? Then obviously your signal path will increase. But so there is always a golden balance you need to strike on the look angles. So that's what I've added a comment. At higher distance, typically this is applicable if it's a geosynchronous satellite or those GNSS, because then the distance is very high, but then your look angles will be very shallow and your signals will be subjected then to interference, because you are not the only one who are operating a satellite. In today's world, the space environment is so crowded, and you might have been hearing a lot of private players now getting into picture, right from Starlink, and a lot many will be probably in the next 5 years. You would read the names. So obviously, there is bound to happen an in-band and out-of-band interference, also obstruction from other stuff on the receiver side, which could be your building, trees, and mountains. But more importantly, the challenge I see is I hear is probably the crowd. I mean, you can literally see the satellite which are jamming the orbits. There are a lot of satellites which are not inoperable and which are launched in order to cover the next gen higher bandwidth requirement. Now, you might read the term here, WRAP. It's nothing but our code, what we use for such kind of calculation and engineering analysis. That said, you are absolutely free. You can look up, but I know the fact there are very limited tools available, even to industry. Forget about academia. Sorry, my Fafed, I was academics, and even the academia world is specifically the tool for satellite network coordination or how to define a satellite network. So that's a very niche topic. But if you are interested, just Google WRAP and you might get some, how would I say, based on what limited something slight version which can be still used for academic purpose. So when you talk about coverage, there are three aspects. Satellite coverage I'm talking about, not about general. What is the satellite to ground coverage? What is the Earth station coverage for a specific space orbit or the orbit in which the satellite is moving? Then the third, we already talk about what are the interference between the space station, interference between the terrestrial station. Bear in mind the fact, even if you may not be aware, but recently this has been a bit of a pain point. There are a lot of flights at any given time, at any given moment across the globe, and there are certain sectors which are heavily crowded air sectors. So even the flights or the which are operating right now, they themselves act as a lot of interference for certain frequency band or for certain satellites, specifically for the LEO and MEO. So there's now new technology coming to tackle. Now, for satellite, defining a satellite network and coordinating the satellite network, you have to follow certain ITU standards, and I'm not going into those detail, but there are specific space to Earth propagation ITU models P619 or free space is 5 to 6. If you are dealing with satellite satcom specifically, which cover sea surfaces, but that is more for naval stuff, then you have to follow certain ITU standards. If it is just space to space propagation like satellite to satellite, then you can deal with just free space and line of sight. But just be mindful. Now, how do you create a satellite network? Now, there are different ways. You can write your own code from scratch in any math code. Again, that said, we have Compose. Compose is an equivalent of a free space, open source, something similar to MATLAB, but you can use Octave or any tool to build this, or what we use in the industry is WRAP, W-R-A-P, it goes by name. Don't be fooled with the name, it does a lot of other stuff, but just as I said, image speak more than words. That's how there's a simple toolbox where you can define satellite network. You need to be mindful, first of all, to define like, okay, what is the transmission gain? What kind of satellite I'm defining? Is it a GEO, or MEO? What is the transmit power? What is the frequency band it covers, etc. So of course, you need to populate those information first, and then it will help you to calculate the transmission gain, and etc. I think I need to cover something is the space Earth propagation. So there are a lot of losses. I'm talking in more context with the satellite networks. How do they operate and what aspects you need to consider? Free space loss, that is inherent, is going to occur everywhere. Attenuation due to atmospheric gases. I already talked about beam spreading. What is important is there are certain ITU standards which you need to follow if you want to implement your own codes, or if you are just using off the shelf, yes. When it comes to space to Earth propagation, I'm saying now downlink. Uplink is where you send a signal from, as it goes by name. But again, it's not hard and fast rule. Some people or certain engineering, I would say, nomenclature argue that it's not hard and fast that an uplink signal should be always from Earth to satellite, and downlink is from, it could be vice versa. So I can't take my words back, but just be very clear that I'm talking right now more to downlink, which is space to Earth. So you need to identify whether the space station is visible from point of Earth, how is the refraction is tackled. Then there is a very specific ITU specification from diffraction, which is very valid because your Earth surface is not, yes, I mean, you know, we all know Earth is not exact spherical, but it's like slightly flattened at top and then it's kind of a ogave. So yes, there are certain formulations. When it comes to satellite coverage, what we really look is the footprints. Bear in mind the fact a satellite covers a kind of few hundreds and few thousand of square kilometer of area. It doesn't cover a tiny area bit of, and in that case, the way we measure the coverage in terms of power flux density contours. So you can write your own code or use industry tools. What you are really looking, that is a very basic step when you launch, before you even design, or let's say you have designed a satellite, you're happy and you want to look first, the fundamental aspect is what is the coverage or what is the power flux density, what area is it covering, and is it sufficient enough to cater the traffic. When I say traffic, the number of users which will be then using it as a transceiver. Okay, so we have some coverage tool. The footprint calculator is, I mean, this is available in static condition as well as time dynamic. When I say time dynamic, what does it mean? Hold on, before we deal anything, I just want to run a simple more realistic example. My bad. Funny thing. My. So what I'm showing here is I'm using essentially I'm trying to uh, solve a real world problem wherein I want to deploy a receiver which should tackle in the worst case scenario or any, let's say, natural calamities, but that should be always in line communication. So it might happen in the unlikely situation, but if you have earthquake or flooding or any something, a natural disaster occurs, it's very common that the first and foremost impact is on your communication system. They go down, or you will have a patchy connection, and that's where SATCOM is very reliable. However, you want to ensure that if you want to relay key warnings or key communication says ensure that the if you want to relay the warnings, the key communication system should be up and running. So if you look across globe, this is very common. You will have some non-disclosed site wherein certain receivers will be deployed, which will have round the clock connectivity to the satellites which are moving dependence on LEO, MEO, or GEO. What I'm showing you now here is there is an receiver deployed at XYZ location, but observe carefully. I'm now doing a time dynamic simulation or time dynamic calculation where it shows that over a period of next 60 days or over a period of next 90 days or over a period of 1 year, I want to ensure that irrespective of whatever these satellite it is looking, my receiver is looking at, it should receive or it should be in communication or it shouldn't lose a communication with the satellite. You can select I'm using a GPS band or is it a LEO or PO or whatever. But in real world, now look from the engineering perspective, in real world it's very hard. The only way you can anticipate is deploy, identify location, and then deploy satellite and look. So that will not never work. You will have to have use certain simulation or emulation codes. So what it allows you to do then is it will allow you to define your satellite network or whatever satellite band are you looking at, GPS or GNSS or whatever, what frequency, what band, and then you say, okay, solve it, allow it. I want to now simulate for next 60 days. What satellite is it looking for my specific location? I should have received signal strength above, say, about certain threshold. This is a real world application. Okay. So that's what I was referring to, a time dynamic satellite uh, simulation. Now observe carefully again this slide, so this animation. So this is for a very brief, I mean, the frame rate is accelerated, but this is done for 30 days and it shows that which satellites are visible. Because obviously, if you recall, your Earth's control or receiver station is fixed, your satellite are rotating around, and obviously what satellite it will look for a specific time and day of duration, that will change, and it will also then give an idea. So that's how real world work. Now rolling back to where we are. Da, 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 da. I hope it's clear. I'll keep some Q&A session at the end, don't worry. Where we are. Yes, here is, yeah. What I haven't covered so far is the interference and noise. Now you might question, is it really it is, because in real world you will find a lot of noise which will garble your signal, or interferences wanted or unwanted. And how will you tackle the noise? The only way is then work at the receiver size. You need some filtering. Now, filtering is a very generic concept, but let us be precise, being engineers. You might have heard about this term band pass filter, band stop filter, or does this resonate? What is filtering? Any one of you can unmute and answer. Feel free, or I'm not sure who has the admin control. But does this resonate? Does this make sense what I'm speaking so far?
Yes, it's fine.
Okay, thank you. So just wanted to have a bit of break, and yeah, I'll keep some time at the spare time at the end for a QA sessions. Okay, rolling back. So there are interferences, both unwanted and unwanted. They could be between satellite to satellite or between satellite and Earth station. So you'll have to factor in those aspects. You can't just ignore. Again, how do you calculate those interferences? With the industry where I come from, we have our own tools, which is interference tool. But by far and large, what you really look is you are looking into signal to noise ratio, SNIR. What is it? S by I and C by R. So obviously here, when you talk about interference, there are two aspects: interferer and interfered. Okay. In the real world, this goes with human psychology. I read the other day the article. It's quite nice, but anyway, just sort of fun context. Essentially, you might feel like when you communicate in a group, you might observe there are certain people who will act as interference, and then the other way, you are, if you're on the receiver side, you are interferer, or vice versa. But keeping aside those aspects of the human psychology, if you're talking about interference, there will be always two aspects. So imagine you are transmitting on a downlink frequency of, say, which is a random frequency band, say 4.4 gigahertz, and at the same time you have something uplink. There is someone another who is sending information on a uplink frequency which is very close to this or in the same band. So it's very bound to happen that um, the C band or S band everyone will be using. Or let me put in very simplest context. Let's roll back to the day-to-day example. We all use cell phones. Okay, now it doesn't matter what cellular operator you are tied with. Are you with Idea or Airtel or whomsoever you are? But it is very known established fact that all of the cellular operators, they will use some common frequencies. Have you ever wondered how do they avoid the interference? There are two important aspects: in band and out of band. So obviously someone might argue, oh well, there are guard bands and that what it does. Unfortunately, it's not that simple. Even having guard bands, you will come across with harmonics, frequency harmonics, or yeah, natural resonance, and you'll always get some interference. You might have experienced sometimes your uh, phone connection, you may feel a bit dodgy, you may uh, lose certain words, or sometimes you just are not able to connect. That's where interference comes into picture. However, when we talk about interference, you need to define here two aspects: what is the transmit power, what is the receiver sensitivity in the most, I would say, simplest context, and then you need to calculate what is getting as interferer and what is acting as an interferer. And then once you know that, you know who's the culprit and who is the victim, you can work around to place uh, corresponding, I would say, filtering characteristics. I'll skip this, not required. So the question here is, we have been so far talking is, I have so far haven't touched anything about the how do we consider the received signal from the map data point of view. Believe me, irrespective of when you talk about satellite communication or satellite network, you will at least hear one or twice these terms: geomap data, or because obviously you can't measure physically going across all globe. The way we do in designing is you will need to consider your map data, your terrain profile data, your attenuation based on water mass bodies. So that's where your the term, just refer, ignore the rest of what is on the slide, refer to this vector data. So in satcom or in satellite networks, we use a lot of vector data. Essentially, they cover uh, various kind of map data, terrain profile data, water mass bodies data, and vegetation data, and etc. Blah. I'm not going detail, but it's very important because whenever you transmit or you receive signal in satcom, your quality of signal or SNR is highly impacted by this. So to put in context, let's forget about what's at the header. If you imagine it's an array antenna, okay, uh, and you are transmitting some signal down to earth. Now your main beam will undergo diffraction, scattering, reflection, and your all of the aspects. So this is governed by your terrain profile, the conductivity of your various atmospheric region, and that's why it's important. So typically what we do is a link calculation or link simulation in satcom, and it depends, are you trying to use the satellite service for urban outdoor scenarios or indoor scenarios, or you just want to cater for military aspects. That's a different thing, but you need to then consider all of these aspects: is what are the number of visible satellites, I covered that, what is the power per satellite, how is the multi-path error tackle. All right, I'm not gonna shows a couple of this example. What I'm looking specifically is, yes, this is important aspect. If you are dealing with satcom, you will always end with this term is jamming. I'm just taking an example of GPS jamming, but not necessary. Jamming is involved everywhere for both wanted and unwanted purposes. Okay, and one of the aspect is what essentially jamming does. It you try to transmit on the same frequency and same band, but the key aspect is you need to know the modulation, and that's where encryption and decryption comes into aspect. Apologies for that. Uh, so I haven't covered jamming in detail, but if you are interested, just drop me an email. I can share some open source literature on that aspect. I already showed you this simple video, what essentially demonstrate how the industry tackles time dynamic satellite simulation now, because you need to understand how in real world your coverage or interference is going to work. I haven't even included the interference scenario in this case, but yes, it can be included. Now, again, in the interest of time, just looking, have I missed something? Yes. On the interference side, please be mindful. I should have covered before. Sorry, I'm jumping from slide because the topics are quite vast. You will need to consider when I talk about co-channel and adjacent channel interference, there are a lot of aspects. It's There will be intermodulation effect, image frequency, then harmonics. You will need to wonder about what is my transmitter spectrum. Is it overlaying into another transmitter spectrum from other satellite operator, or even the closest frequency band, or what was that I use in my engineering graduation days? Unfortunately, it's a very famous theorem. Can anyone recall that theorem? Nyquist criteria. Yes, Nyquist criteria. Believe me, Nyquist criteria is still used and valid specifically for SATCOM, but even in general, uh, I would say communication blocks. Receiver blocking and receiver selectivity is another topic. If anyone is interested, you can pick that, and there's a lot of work to be done. Yes, there has already been some work done in the past, but we probably joke in our industry world is, if you want to really mint money in like millions, just work on the receiver side, because it's saturated, but it's still a lot of things haven't been resolved on the receiver side. You can use any tool to calculate what will be the potential frequency that might interfere on your system or whatever satellite. Let's say in tomorrow, who knows, some of the attendees, they may work in any organization, or you decide to start your own startup and want to launch your own satellite, but you need to think out, okay, what are the potential frequencies which may interfere? How do I mitigate these interferences? Are there any different approaches like frequency hopping and direct sequence? This very age old and been rugged. I covered this. Give me a second. So that, again, I'm just being mindful looking at the watch I have set up on my screen. So these are the very high level aspect I wanted to cover on the satellite network. Again, this is not everything. It's just very high level. Okay, so what I'm gonna do is now uh, roll back to the another aspect of this is something on the battery. We haven't covered anything, as I did mention, so I'm just gonna roll back. This is something I work in the past, is battery management system for satellite. As I said, human being, I mean humans or animals or mammals, doesn't matter, or any living creature. There is a saying, some people what it says, like, I don't want to deviate, but rolling back, if you don't have a, sorry, excuse me, my PowerPoint is behaving funny. I leave this as it is. Ignore what are the tools at the bottom. What I want to show here is most critical aspect is how are you gonna tackle the battery system or battery management system. It is very key. If your battery dies out, your satellite stays into orbit, and it becomes literally what we call as a garbage. Yeah, what you might have a space garbage or space junk is nothing but the satellites which have died away. In This is the most critical part in satellite, I would say, communication, and rather again most ignored. Unfortunately, the syllabus doesn't cover is how are you gonna handle the battery. Your end goal is, now you might be familiar with the EV terms. Everybody's talking about electric vehicle, blah blah stuff. By far and large, the physics applies the same, but you have to be mindful of how your battery is gonna work with the number of charging, discharging cycles. What is the state of charge, associated state of health? Bear in mind the fact every time your battery charges, it has to uh, literally overcome the internal resistance of on the ionic level, and then that's why, if you have ever wondered, let's put it simple, the battery pack, it the battery technology has advanced way ahead. I don't want to complicate. Look at this image. Those are individual battery cells. Doesn't matter is it AAA or AA or what, or the industry standard is slightly different. However, if you have ever used a rechargeable AA cells, if you plug in to the charger, it may get warm, or sometimes it pretty much get heats. That is because every time you charge, it has to overcome the resistance and move those ions to a certain level, to positive and negative threshold, so that you can reuse. Obviously, the batteries in satellite are in physics pretty much, or in theory same, but you need to consider design of your battery pack. I will be very honest, the battery technology is standardized in terms of the individual cell. What is not standardized is, and it is up to the end user as electronic engineer. How are you going to stack those batteries? How are you going to charge? What kind of inverter circuits you're going to use in order to optimize the performance of your battery pack so that it lasts for say next 4 year or 5 years, and everything is very design critical and sensitive when it comes to satellite, because once it is launched, it's on its own. You can't. There are very limited options where you can physically send something and fix it. It has to be auto. I would say, I mean, what to say? There's a hard reset and soft reset, but that's how it should be. So when it comes to battery management system with satellite, it's critical performance and optimization, safety. How are you gonna consider if you want to do rapid charging, but you need to have over voltage protection, over current protection, over charge protection, and also over discharge protection. Remember, the battery is driving some load. That load could be anything. It could be an demodulator, modulator circuit, or it could be the antennas on board. It has to transmit as well as receive signals. Obviously, that requires uh, inverter circuit which will convert your standard battery DC voltage to some 48 to 12 volt whatever, and vice versa. There will be certain equipments. Yes, a satellite does work with certain electronic equipments which will work only with AC. Not all everything is DC. So you'll need an again inverter from DC to AC. So obviously whenever you talk about DC to DC conversion and DC to AC, there is certain loss. We don't have 100% efficient power converter. Otherwise, if you know or you invent, you would definitely mint a lot of money. Rolling back, and then how are you gonna work on multi-cell management? Remember, in real world, we talk about battery pack, but the most convenient way I don't have. I just dissected a. You might again. I'm not promoting specific brand, but I just had a Ambrain power pack or power bank, and it just went bad. Being an electronic, I just decided to open. There was just some loose connection, some few solar dots. I just replaced one of the resistor, very standard, and it was up and running. I believe in the recycling, but that's a different story. Rolling back, remember, it doesn't matter. Are you looking at a battery of a EV vehicle or one in the satellite or wherever? It is never a single pack. It's always individual cells which are arranged in particular fashion that will give you a desired voltage or current required to drive your system. Now, again, what we use is in-house our embed code. It has straight away a built-in GUI, and you can use any platform. You can literally use J. In my days, I use JTAG. Nowadays, everything is USB and peripheral. You can use a USB connect to Raspberry Pi or microcontroller. You can develop your in-house battery management system. What you need to be mindful is specifically just how are you going to tackle multi-cell management. I'm just going to skip something again in the interest of time. But look, there are there are a lot of off the shelf, I would say, development boards and microcontroller. You can use any one of those. I'm not promoting, but the most reputed are Texas, Infineon, ST. But as a graduate, or maybe if you want to work out with your B project or master's project or whatever, even PhD, you can just pick up Raspberry Pi, cascade a couple of them, and even build a battery management system. What I want to show here is the important aspect you need to consider is overcharge protection, under over discharge protection. So what we have is embed is just a tool. You can use any tool. Honestly, you can Google battery management system tools. There will be a lot of available. From what I have used in my projects or what I've been is this is embed GUI. So it's you just launch it's installer.exe, and what it does is, and I typically prefer is if you can see, then it's more easy to diagnose. Believe me, designing is a different aspect, but diagnostic is way time painstaking and time consuming. So what I'm doing now here is essentially I've developed a GUI, it's an embed GUI. I can through a UART or just through the USB interface, I can connect to my Raspberry Pi board, and it's a very simple. In this case, a Texas board, okay, and conventionally it was through JTAG, but now we have allow it to communicate through any high-speed UART or ISO UART. Is anybody from embedded background? He can easily relate what I'm talking right now. So what I'm saying is you can develop your own simple, very simplistic form of battery management system. You can interface with embed and try to understand, okay, if I'm now charging with say 12 volt 500 milliamps or 16 volt and 800 milliamps, so it's just my setup in the lab. You can ignore. You can use any vector network analyzer or anything. What I want to show here is most critical is when your battery is charging, what you need to monitor as easily available is what is individual cell volt you are monitoring, also the temperature while the battery is getting charged, and vice versa when it is discharged. What is the reason I'm covering the battery management system is what if a fault occurs? Let's say a particular individual cell is not charging, or it is charging very slow, or maybe the temperature is rising very fast. That is where we have something fault EVM detection. It will pick up, it will literally blink a red dot in front of that specific cell. Now remember, this is user defined arrangement. So you might wonder like why are there so many cells displayed on the faulty EVM GUI, whereas here I'm just showing probably just it's a 16 by 1 matrix or 8 by 1 arrangement. This is a prototype board, and as a student I will probably love to work to define my cell arrangement, my own configuration. So embed has a GUI. You can use any microcontroller board, be it Raspberry Pi or Pico controllers. There's a lot of available in open source, or the professional would be then Texas and other stuff, etc. Uh, allow me, excuse me. So that's what the GUI does. But as I said, it will allow you to monitor the temperature while the cells are charging, also as discharging. You can also add an external load to force discharge with a high. Let's say there could be a requirement of certain communication system to pump high power. Obviously, in that case, it will withdraw battery or surcharge for that specific device. So obviously, you can change the load and see what if the current is, or the battery is getting discharged at a higher rate. In that case, is my temperature rising? Is it ambient? Is it okay or not, etc.? That can be also work around. Any questions, or has any one of you work on battery management system, or that is not consideration at all? And but could be a topic of interest if you want to. And this is generic. Your battery could be used for a drone. Your battery could be used for how would I say, EV vehicle, or it could be used for any hybrid powertrain, or even satellites. Purely they operate on batteries. But of course, this is a very high level stuff I wanted to just cover. Does that make sense? Anyone can comment. Is it relevant, or just have a thought at the back of mind? You can work on this engineering aspect as well. Okay, I'm not going in detail, but there are a lot of stuff. Yeah, what I want to cover now, the next topic is something on the power converters. Okay, so I talk about the system power supply design suite. So my background, yes, I recall my graduation project was on, I'm not sure if Professor Mangate is still there, but he was my guide those days in 2006, and we made some ultrasonic motor. Probably we even won some IEEE prize. That's long, long back, probably now 2006, so long back, it's almost 18 years ago. But what is critical I want to mention here is um, a lot of people completely ignore and they just jump into VLSI. If it's not, I haven't covered. We do work on defining the gate layout and diagnostic of the gate level and RTOS level, but I'm not covering that in the SATCOM. What I'm covering is the fundamental aspect, the power supply design suite. Have you ever wondered how is the power supply designated for individual equipments operating on board of a satellite? You need a power converter, which is nothing but an LLC converter. So essentially, as I said, you will require to consider the aspect of, we haven't explored, believe me, it's a quite big market, a DC to DC converter or DC to AC converters. There are again a lot of tools available in the market. You can use Plex, which is an open source, or what we use is a PSIM. It's an industry standard. PSIM is also available if anyone want to explore. I want to just come out, is essentially is a built-in template. You can drag and drop and quickly convert. What is essentially a power converter is, okay, let me be very clear and simplistic. Bear with me with some of seconds. I hope my camera is on still. This is my adapter of my machine or the laptop I'm using. Probably we all use, it's nothing out of the world or any not alien concept. This is nothing but the power supply design. So this has an inverter inside it. So inverters are present all around everywhere. Even the charger you use to charge your cell phone, it's a very basic class A, class B. Will have some bridge rectifier. Different. We all have studied probably class A amplifier, class B, class C. So it's nothing but cascading of your different amplifiers. The catch here is when it comes to power supply, they use IGBTs, NAND IGBTs and GAN kind of chips. We do support because it's the industry tool, PSIM what we use. It has built-in library for different IGBTs and GAN. You can drag and drop. You can simulate, look at what is my output response now. Is the signal condition? Can I change? So you can literally define, this is what my output goal is. These are my input, DC inputs. And there are built-in template you can drag and drop and generate built-in electronic circuit for DC to DC converter or DC to AC. Does that make sense? Have you touched this base? But just bear in mind the fact there's a huge market and appetite for DC-DC converters or DC to AC converters. I agree there are a lot of established players, but there are a lot of things to be done specifically on signal conditioning algorithm, or if you come out with more innovative design, like even if you say that instead of using 4 IGBTs, my design now uses just 2 or 3, 2 will not be possible because based on what is driving, what the load is, even if you try to reduce one of the LC loop, yes, it will save a lot of cost because these inverters are produced sometimes in mass scale or they will cut down. I mean, that's where the industry is driving low power efficient or power efficient or efficient power converters, put in simplest. Second aspect is how are you going to tackle your EMI? I haven't even touched like EMI EMC is a big problem, and there are very few, I would say, expertise even within, I would say, specific region, geographic region, or even within specific industry. So when I talk about EMI, it talks about radiated emission, radiated immunity, and conducted emission. For now, let us stick to conducted emissions because we are dealing with circuits and power converters in clearly. So let us say you design an DC to DC converter. However, the first and foremost question, at least in SATCOM or anywhere they'll ask is, okay, is it complying with CISPR 25 class A, B, or C standard, whatever it is? And then you would argue, well, how do I know? The classical ways, you prepare a breadboard. I remember in my engineering days, there was a, sorry, excuse me for the burp. I haven't my lunch yet. I've just been back-to-back meetings. Yeah, rolling back, what I mean is network and lines. There was to a subject, network and lines or network and theory. So you used to prepare some breadboards, prepare some basic circuits, test, and then you look what is the output is. However, that's not the interesting thing is if you don't have access to any simulation emulation tool or any design tool, the only way then left is, but be mindful, it is very hard to prepare a breadboard kind of circuit or even a prototype because you need to source these devices physically, those hardwares, the resistor, capacitor, IGBTs prepared, and then sent to a test lab. A more, I would say, wise way or from an engineering perspective is use any power electrical simulation tool. I leave it to you, whichever you want to. PSIM is what we use, but that said, you are free to use anything. And what it will allow you to do is, once you are happy with your DC-DC or your electronic circuit, doesn't matter whatever it is. Let's say it's a simple class A amplifier, class B amplifier, but you want to understand, is it complying with CISPR standard or conducted emission? What the tool will do is it will just run some, essentially it will just solve and tell you, okay, look, your circuit is now, your emissions are way above class A, class B filter, or emissions are above class CISPR 25 class B, let's say for sake of argument. So how will you fix it? You will need to add a filter. The question here is, if you start doing hand calculation or even with some MATLAB codes, you will end up with days or weeks because the real world circuits are way complex nowadays. The only way to approach this is, I would say, use such kind of tools. What it will tell you is it'll tell you exactly, okay, you need a filter, what kind of filter, an L type, say inductor capacitor, or pi type or a T type filter. So these are most common filters used to suppress conducted emission noises on your circuit level. When I say circuit, it's a generic term. You have as complex circuit with a number of branches and all kind of devices. So it's the end user choice. I can use a pi type filter. Pi type filter will have at least 1, 2, 3 devices, 2 resistor, 1 capacitor, or 2 inductor, 1 capacitor. But looking at the mass scale production required for such kind of circuits, I would be mindful. I will use an L type circuit. I might need just 1 resistor and capacitors or 1 inductor and capacitor, because lesser the number of devices or hardware, resistor and capacitor or inductor you will use, it is more cheaper and efficient. That said, it may be the case that with a pi type filter, you will get the best rejection. For example, here, the one in the middle, L type or T type may not give the same rejection, but as long as you are complying with the EMI standards, job done. Why would you like to spend extra money if a L type will give the same, L type filter will give same response, okay, or say will suppress your noise, okay? That's where it is comes to. Second, the last aspect from the power converter side is the motor control. You might have heard this term all around. Again, I'm not referring to EV, but even in satellites, they use a lot of micro motors, micro to macro motors. So most of those are DC by default, but you need to figure out some efficient motor control algorithms. So it's up to use. The classical is maximum torque per ampere or maximum torque MTPA or MTPV. These are classical configuration. But again, you can design or define your motor control algorithm from scratch, or there are some built-in templates in MATLAB or any other code. Again, I'm not proposing to these because MATLAB is very expensive and they sell only with toolbox. Rather, I would vouch there are a lot of open source code. Go for it. That is way better. And what we use in industries, as I said, PCM is the tool. If you're interested, just look at the website. You can get a trial license as well. That's it from my side over here. I will take a break and being mindful because I want to spare some time for Q&A. I'm just looking at my clock. Sorry, give me a couple of seconds because I'm in a different time zone and okay, we still have some time left. So what I'm going to do is I'll spare some time for Q&A. What I want to cover is an important aspect I haven't so far is yes, I have designed PCBs in my job role a lot, but what is most ignored term is and typically signal integrity, power integrity, and that's what I deal as electronic engineer. The most important aspect when it comes to satellite communication is this one is the multi-physics optimization of your PCBs. This is a completely ignored aspect, but if you go to industry and if you want yourself to be employable, hireable, whatever the companies have available, especially within the engineering domain, believe me, they will ask, have you any experience or have you dealt anything with multi-physics on electronics? When I talk about this, like designing PCB, you have a number of tools and they are way optimized. You can just say that I want to design PCB for, you can say for a signal conditioning or probably a audio amplifier or class A audio amplifier, or you can just give and the PCB design tools are so mature these days. They have already have AI introduced wherein it will give a nice layout track and say, okay, put this device is the user's call, then what hardware he has to use. What I'm talking about is specifically the combined performance of your PCB, your structural plus thermal management. So these are what aspects considered in satellite. So remember, your PCBs which are used in satellite, they are subjected to very stringent standards because imagine when your satellite is launched, it is subjected to very high stress, strain, and what I would say centrifugal and centrifugal forces. It has to sustain those, so they use potting material, and it is very key to understand what kind of stress strain will be subjected to your PCBs. This is I'm talking about the real world engineering aspect. How are you going to tackle steady state heat transfer, transient state heat transfer? Those stuff. I understand if you are from electronics background or electrical, this may not be relevant, but this is where the industry is or requires multi-physics simulation. So probably you might ask, okay, why, why am I bothered or I'm connected? You are, because if you are designing a circuit, and let's say there could be scenarios one of your resistor or capacitor goes off of dies, it may be an open circuit or short circuit, and there may be a sudden current discharge over this PCB trace or a netlist, and it may further hamper the original performance of your whatever the circuit you have implemented on the PCB. And in that case, what might happen is it may generate a local hotspot, and it may bend the PCB, or yeah, I'm not touching those aspects, but believe me, what we deal at engineering level is solder fatigue. So a picture speak more than word. I'm just gonna escape this and show you just one slide. Yes, we all have seen PCBs real world, but have you ever wondered if it's a microprocessor, how the pins are connected? If it's a simple NAND chip, NAND NOR gate chip, say 8 pin or 16 pin, that's a different story then. But however, look at the engineering aspect. These PCBs and the devices, they are subjected to very high stress strain when they are launched into space. Once they are into the space, that's a different story. You have vacuum and there is no way for convection. The only way the heat dissipates is through radiation a little bit, but conduction and convection. So you need to be mindful of how you're going to tackle those thermal aspects of the problem. And bear in mind the fact I'm referring to the thermal problems created from, I would say, electronic circuits. So it could be a high surge of current or voltage or unbalanced load or something, the resistor just dies off or capacitor dies off, and that's where this thermal hotspot will be generated due to high surge of current and yeah, unbalanced voltage. So I'm just showing like these are different configuration. Of course, don't worry about this complex engineering problem. You can start with something very simple. But what I'm saying is this is where the in at least in satellite networks and satellite communication, this is a very critical requirement. How would you tackle EM plus thermal or electronics plus thermal problem? So we use a tool called SimLab. There are a lot outside across the globe. Because very critical is you need to predict the failure criteria, when will, what could be the conditions, or after how many number of operations or cycles, or switching on and off, or let's say the clock cycle of, let's say you have microcontroller operating a certain clock cycle, say after what span of continuous operation you may have a solder fatigue, or a solder may fail, or probably your PCB or your IC may die out. So you need to predict that. It's called predictive analytics. It's very common in manufacturing. Historically, it's come from automotive manufacturing environment, but it's also now relevant for uh, high stringent, I would say, engineering equipments, specifically the electronic equipments and designs and PCBs which are used for satellites, as well as any MIL standards. So that's pretty much from my side. I'm gonna stop sharing my screen. I'm aware we are a bit short of time, but any questions or comments, please? What I've tried to cover is a couple of aspects within the satellite networks. Again, within the satellite communication, you have a lot of non-radiating passive and radiating devices. I haven't covered those, but I've just given you an insight of how machine learning can be applied. You can use, as I said, any tools. You're free, or a couple of them I have mentioned on my over the fly. You can just Google if you are. Some of those are available as light version, or you can check as well what is accessible. But any questions or comment, please? Okay, so there's a silence. I'm not sure. That means two. Either what I spoke is completely unrelatable. I said, oh, just couldn't digest anything, or I take the other way. Okay, everything is good. But yes, please, any comments? I understand different people have different mindset, but if you are not happy to speak, maybe you can write back or comment to Professor Kai or any of the faculty. Yes, feel free to write. It's fine. We have a, I mean, as the human psychology goes, I'm quite pretty open to talk and ask questions even open and forums where you have maybe more than 100 of people attending. But if you feel, if you're not comfortable, absolutely fine. Please drop an email or just give a feedback. How do you feel the session was? Any comments or questions?
Participants are requested to ask questions if you have any doubt.
Okay, you might need to unmute the participant. Well, I'm not the admin, or I don't have any control, so sorry. But you can type if you want quickly.
Hello,
Because I
sir.
have a yes, go ahead.
Can you explain how the mathematical modeling can be done for antennas or any other devices?
Yep. So you can use how would I say? When I started long back, I used Fortran, but you can use C++ for coding, or the most easiest way is you have access to a lot of simulation tool, or probably you'll then use to access any toolboxes, open toolboxes available for RF. But in general, when you are looking as a math model of antenna, what you are looking is the impedance extraction and the source, okay, and how is the I would say other material properties. That's what you will need to consider for a math model. But I would say the straightforward way is just look for any simulation tool. There are a lot of available in market, open source, or if you wish you want to, I'm not sure what are accessible at your end, at your I would say academics, academy or specific institutes. Just check those.
So for this, only the specifications or the any other environmental parameters we need to consider for designing the such type of antennas?
To begin for with the antennas, I won't consider the environmental parameters because that comes into propagation and network. That is more on system level. If I just want to design the antenna, I would start what are my key requirements. Like I would look what I'm aiming, what should be the VSWR reflection coefficient and what is the gain, first of all. Then based on that, I will look what frequency band and what is the bandwidth you want. So you need to, first of all, list what are my input design criteria, what are my output requirements, and based on that, then you can figure out what antennas are best suited. Are you looking for low power devices, or are you looking for high power, or yes, depend what is the application. But environment I will consider way later, because typically the antenna is designed and solved on its own, considering your surrounding environment is vacuum or free space. That's how the standard approach is. Then later words you can move it and place it in a, let's say, outdoor scenario or a indoor scenario. Yeah, that's a different aspect. Yes.
Okay, thank you,
And
sir.
then you can include, like, so we do include atmospheric attenuation, or what if the moisture content changes or rainfall, but that's more on to the propagation side, network planning and propagation side. That would be a later stage. I would just consider antenna on its own to begin with.
Good evening, sir.
Yes.
Sir, to start with antenna design, like optimization, you said so many parameters. So to start with, what type of antenna we can start, sir, in the beginning?
That depends what I mean, what is like, are you dealing with for automotive or naval, or what kind of application? Is it short range, medium range, or low
Yeah,
power
for
devices?
wireless communication. Wireless communication.
Yeah, but is it for ISM band 2.4 gig or 1.8 gig? How it will literally depends. There are a lot of
2.4 gigahertz ISM bands.
well, ISM band, it's very saturated. In case of ISM band, I would say you can start with classic monopoles or patch
Okay.
antennas. There are a lot of patch antennas available. But the
Okay,
question
sir.
is, for, again, with the ISM band, are you looking for, like, I'm not sure, Bluetooth, LoRa, Zigbee? What is the application? Or is it just for Wi-Fi, or like short range communication? Or even in ISM band, you can use it for like up to few miles, a few kilometers range as well. Like if you look at the IoT devices, a lot of IoT devices, to make it license free, they use ISM band, but they cover reasonable 5 to 6 kilometers easily. But if you look at the classic ISM band like LoRa or Zigbee or Bluetooth, yes, they are very short range, probably just up to 10 to 15 feet or 60 feet, or less than that. Yeah.
Thank you,
So
sir.
yeah, with the
Hello,
patch
sir.
antenna, yes, go ahead.
Which tool you suggest out of, let's say, HFSS or I3D or CST micro bench or any other to design the antennas?
Well, it's completely your preference, I would say. I won't recommend any specific tool, but I3D probably is absolute. It's not even, it doesn't even exist now. I3D was when probably I was doing the graduation. That tool has ceased to exist. All are good tool. I mean, it's really your call. If you want to use HFSS or CST or FICO, each one will have different learning curves. So yeah, I mean, I can't say use specifically this tool. It's entirely your call. Have a go. I mean, yes, whichever is easily available and what fits your requirement. But yes, I mean, we use quite a wide range of tools, because if it's consultancy, then you can't stick to just one tool. Sometimes you have to just use in-house tools or off-the-shelf commercial product. Like we use FICO in our case, but yeah, you can use any of other tools.
Okay, thank you, sir.
All right, just a minute left, but have a look. I mean, there are a lot of aspects from satellite networks or battery management system or even power converter side. So a lot of stuff, topics you can look into. All right, if that's it, then sorry, I have a hard stop. Again, thank you very much for the opportunity. I'm very privileged to give a short talk. I haven't covered all and each aspect, but hopefully that was uh, pretty much informative. Thank you. I'll have to leave the call now. Thanks again.
Uh, uh, Thank you, sir, Mr. Swapnil Kulkarni. On behalf of organizer and participant of this faculty development program on next generation communication, so we would like to extend our heartfelt gratitude for your enlightening session on space communication and satellite network. Your expert insights and engaging presentation style made the complex concept accessible and fascinating to our audience. Your passion for this subject is truly inspiring, and we appreciate the time you took to share your knowledge with us. So, thank you once again for your outstanding contribution.
Right. Thank you very much. As you say, Avari out, where I come from, the place. Cheers. Bye bye.
Yeah, it's okay. There is a light failure in the college. So once again, thank you to Mr. Swapnil Kulkarni. And let's welcome our next guest, Mr. Shridhar Prabhuraman. So let me introduce first. Sridhar Prabhuraman leads research and operation at the Maritime Research Centre, 9, Sydney, Australia, bringing over 6 years of experience in underwater acoustic and maritime research. With a master's in artificial intelligence from University of New South Wales, he specializes in underwater ambient noise and its impact on maritime security, sustainability, and the policy. His work reflected in multiple notable publications and focuses on leveraging artificial intelligence to enhance underwater domain awareness and drive innovation in the field. So I welcome uh, today's resource person, Mr. Sridhar Prabhuraman from Sydney, Australia. Over to you, sir.
Thank you so much. Let me share the screen. Right. Right. So again, hello everyone. My name is Shivnagar Prabhuraman. Today, I represent the Maritime Research Center. After the last session, I find myself in filling in some big shoes here. Understanding the August gathering that we have here of excellent researchers and people and doctors. So most likely, the kind of topic that I'm going to be sharing today, hopefully, is of some relevance to the gathering. So we'll essentially start this presentation. I would like to go through some basics of underwater acoustics. It's not a domain that is widely recognized. It's not a domain that is widely catered for. So we'll essentially go over some of the basics of underwater acoustics, and of course, looking at what are the communication aspects of it. And then we'll talk about one of the major aspects that concern the underwater acoustics, one of the major impeding factors that concern the underwater acoustics, which is the underwater radiated noise factor. During this presentation, feel free to stop me. And if I yawn in between, I apologize. It's 1 a.m. in the morning. Not an ideal time to make a presentation. All right. So let me begin. So underwater, so sound is one of the most important form of communication underwater. This is primarily because light does not travel very deep, and there's a lot of attenuation that happens. And as such, acoustic medium or sound medium is considered to be the most notable and the widely used forms of communication. However, that does not mean that there are not other forms of communication available. When we talk about underwater communication, we essentially look at 4 different aspects: the acoustic communication, the optical communication, the radio frequency communication, and the magnetic induction communication. We'll go over all the 4 in short, but we'll primarily focus on the acoustic communication part of it, considering it's the most widely used one. So starting with optical communication, as the name suggests, optical communication uses light waves, typically in the blue-green spectrum that we look at. And it essentially transmits the data between the underwater devices. The problem here is that the light wave will be traveling in a straight line and they will require a clear medium to propagate efficiently. That basically means that if you have a turbid water, there's going to be a sense of difficulty in the communication. Now, this method is basically similar to fiber optic communication, but basically without the cables. We use lasers and LEDs to transmit the signals. The way it works is that you can think of it like from an analogy perspective, you can think of it like a Morse code. A light source, being an LED or a laser, will generate some modulated light pulses, and the receiver will capture these light pulses and convert them back into electrical signals. And then the variation in the light intensity, wavelength, or phase will essentially be the one that is responsible that will send the data back. In terms of the pros and cons, again, as I mentioned, you will have a high data rate. It essentially means that because you're using light source, it is capable of transmitting large amount of data. The signal propagation will be faster as compared to the acoustic communication, again, which is notably the widely used one. And of course, uh, as compared to acoustic communication. So when we talk about anything underwater, we need to understand that a lot of applications underwater is either uh, uh, naval related, or it is either marine conservation related effort that we're looking at. And in that perspective, it is a secure communication is less susceptible to any eavesdropping compared to radio frequency or the acoustic signals that we have. However, because we are talking about light, the effective range is typically less than 100 meters, because again, as I mentioned, light gets absorbed in water very quickly, and that's the reason why it is not something that is widely used. To the matter that even you can see that most of the marine mammals, whales and dolphins, everyone, they do not use, I mean, they don't see things, they essentially hear things. They use the concept of, they're similar to the concept of sonars that we have. They use the concept of echo sounding. They identify things via hearing stuff. They send a pulse, the pulse hits the object, it comes back, and based upon that, they identify the object that is present in the region. Um, Now, this using optical communication, it is again affected by turbidity. If there are particles that are suspended in the water and any kind of marine organisms, all of that will cause severe attenuation. This also means that you need to have the sender and the receiver precisely aligned between each other for transmission to actually happen. Now, this is in a very shallow water region, or in a very in a particular condition where your receiver and sender are just below each other, less than 100 meters. It's very easy. I mean, it's probably most widely applicable. However, the applications as such where this is used is again it's very, the real world applications where it's used is very narrow. Like for example, it can be used in underwater autonomous vehicles. So for example, if the autonomous vehicle is in at a certain distance, less than 100 meters from your submersible or your surface support ship, in that case you can use this. Again, high speed of exchange rate and all those kind of things. So all the subsea infrastructure monitoring that we use, so we know that a lot of internet and everything that we have, these are basically, we have subsea cables for most of the internet that we use nowadays. So monitoring of these, so if you can send a device towards the depth of the ocean. So basically monitoring the seabed infrastructure, it requires a high level of video feed and everything. And all of that can be applicable. That's again one more application for optical communication in this particular sense. Moving towards the next one, we have the radio frequency communication. Now, the basic concept of radio frequency communication is that it uses these electromagnetic waves to transmit the data wirelessly underwater. So in the air, the radio frequency waves can travel long distances. But in water, they are rapidly absorbed, especially when we are looking at something called as a seawater, because seawaters usually have a high amount of electrical conductivity, and that's the reason why they are rapidly absorbed. And therefore, again, this is again something that can be only be used for a very short range kind of an application. Um, Again, the concept is simple. An antenna will transmit an electromagnetic wave. The receiver will basically detect these waves and decipher the encoded data, whatever data that we are transmitting. These data again will have to be modulated, time domain multiplexing, frequency and phase variations. All of these will need to be added. If you want to look at it from an analogy perspective, again, this is similar to a Wi-Fi or Bluetooth signal, but much weaker, because again, underwater, there's a high resistance to radio frequency waves underwater, and therefore it's not something that is highly, it's not something that sends a huge amount of data. One really good application of radio frequency essentially is AIS communication. So what happens is that when we are looking at sea, so the way we have GPS in our mobile devices, which basically tells us that what is the exact location that we are in currently. In the sea, we have something called as an AIS transponder. So AIS transponder is basically an electrical device which is fitted onto every ship. So there is an IMO guideline, and there's an IMO recommendation as says that everything that is 300 gross tonnage and above, basically large vessels like cargo vessels, all those kind of vessels, they will essentially need to fit these transponders. And the way it works is that these transponders essentially send information about the ship to the lighthouse. Lighthouse essentially is basically again an antenna that is present, a receiving antenna that is present at the port side or at the any of the military area, or to the satellite. Both of them uses radio frequency for the same. Um, again, because this is the air-to-air communication, this is much more feasible. If the same can be done underwater, it won't be working. But then again, these ships use these radio frequencies to actually communicate their position to the receiving antenna. And that's how we can essentially see where the ships are, at what position they are. And the kind of information that they essentially send is about what is the location of the ship, what is the speed with which it is moving, what is the estimated time of arrival for the ship, what is the speed, what is the course over ground, and all those kind of things. And a lot of that can actually be used to track a particular vessel. Um, However, in water, they are extremely short range and therefore high attenuation. It's not something that we can be used. Um, Even if we want to use it, it requires a huge amount of power to operate, and therefore the power consumption is extremely huge. And of course, we've established that deep water communication is not something that is really possible using radio frequency much. Right. So coming to the magnetic induction, this is something that sits between the acoustic, uh, in terms of the feasibility, in terms of the range. This is something that sits between the acoustic communication and the radio frequency and the optical that we saw. Essentially, this one uses oscillating magnetic fields to transfer the data between a transmitter and receiver. And since these magnetic fields are not significantly affected by water, like the radio frequency waves, they work better than the radio frequency for the submerged condition. So the idea is that a transmitter coil will generate a time varying magnetic field, and the receiving coil will essentially detect these changes and convert them into electrical signals. Um, Again, think of this as the way we have those wireless charging that happens in our phone. We basically keep our phone on top of wireless charging mat, and essentially one coil will generate a field and the other coil will pick it up. That's pretty much the concept behind magnetic induction communication. Right. So the core of the whole uh, industry in terms of the maximum amount of the most used amount of communication method is the acoustic communication. Acoustic communication basically uses sound waves to carry information through water. Now, unlike uh, unlike light, sound propagates much farther in water than all the other forms, electromagnetic waves and everything, and therefore it is the most widely used. And it is also now good to note that the speed in which the sound travels, it's so if a sound travels at a 300 meter per second in the air, it travels at 5 times that speed in the water. So it travels much more faster in water as compared to air, which is nearly around 1500 meter per second. Again, it essentially works for both low frequency and for long distances. And it also works at high frequency. Again, the distance gets shortened because obviously the frequency is high, but again, both of them can be used. The way it works is that a transducer, basically like a speaker or something, it will generate a sound wave, and these waves essentially propagate through the water, and they are picked up by the receiver. The data that you want to transmit is essentially modulated using the amplitude, frequency, or phase variations again. If you want to look at it as an analogy, you can look at it from the perspective of the whale songs or the sonars or things like that. So if you look at the sonar ping, the how the signal transmits for a long distance without being detected, that uses acoustic communication. The only downside for this essentially, however, is that the data rate is much slow as compared to your optical or radio frequency communication. It is much more slower, and there it will be affected. It does get affected by the water conditions. So notably, the environmental factors that we have, we'll look about it again in the upcoming slides. But we have a lot of environmental factors. Whenever you emit a signal in the water, the water has its own temperature, its salinity, the pressure, all those kind of conditions do affect the how the signal gets propagated, how much reflections happen, how much refraction happen, how the signal bends. The absorption, the type of sediment will also rule in the kind of absorption that will happen due to the sediment and all those kind of things. So environment factors do come into picture here, but yet still, it is better for underwater applications. Uh, the reason is that it is the based range performance trade-off. It balances the range and reliability, making it ideal for military and scientific applications. And if you want to operate in, again, like unlike the above water environment, underwater environment is not something that you have when, specifically when you're talking about sea and like a deep ocean. The environmental condition is not something that you have in your control. So most of the time, the water is going to be turbid, and you want a technology that can work through the turbid water. So unlike other methods, this is not affected by the water turbidity or salinity. And of course, the power consumption is much more lower because it requires less energy to propagate over the long distances. Yeah, and the core concept behind this again comes from the whole how the marine mammals uses echolocation to find its prey. The core concept behind acoustic communication relies on the same. Right. So let's look at what do we actually mean by the concept of acoustic propagation. Um, when we talk about acoustic communication, again, that's basically acoustic communication requires propagation of sound signals, and that propagation of sound signals essentially refers to how the sound waves will transmit across the water while interacting with all the different environment conditions that we have. Again, as I mentioned, the salinity, temperature, and all those kind of things. So if you look at what are the different factors that affect sound, again, as I said, the speed of sound majorly determines how the sound will bend, how the sound rays will bend, and how the interaction will happen with the surface in the bottom and the water environment and such. Um, Now, in warmer waters, where the temperature is more, the molecules will basically vibrate more quickly. And that will essentially mean that the sound waves will essentially pass through them rapidly. And for every 1 degree increase in water temperature, sound speed can increase by about 4 to 5 meter per second. Now, when we talk about salinity, and this temperature is the most important factor, we'll talk about that again. Now, salinity or the concentration of dissolved salts in water also influences sound speed, although it is less significantly when in comparison to the temperature or the pressure. Again, we are talking about deep water here. Now, if there is an increase in the salinity level, it will increase the speed of sound. So higher the salinity level, more the speed of sound. And similarly, the surface water near the equator or in the shallow coastal areas often has higher salinity, while fresh water from rivers reduce salinity near the river mouths and things like that. So it's always near the coastal areas, we'll obviously find a lot of salinity. Um, Now, there's also the concept of pressure. So as we go deeper, the pressure of the water increases, and as the pressure of the water increases, so does the speed of sound again. More pressure, it means that the water molecules are compressed, and with the compressed water molecules, the speed of sound again will increase. What you can see on the top right hand side here essentially is the speed of sound map that we had created for the Indian Ocean region. As you can see, the range of sound speed essentially varies from as we move from top to bottom. There is a variation in the range of the sound speed from 1,534,500 34 meter per second to 43 meter per second, around 10 meter per second difference. Right, and this graph essentially showcases, as I mentioned, as the temperature increases, there is an increase in the speed of sound. So if the temperature decreases, so does the speed of sound decreases. Right. Okay. Before moving forward, in an ideal condition, in an ideal world, when we are performing some kind of a calculation, we need to understand that all the three factors combine to actually determine the speed of sound. So essentially, what happens is that uh, temperature has the highest impact of all the other two variants. So essentially, on the surface of the water column, or if you let's say 0 meter depth or at the surface, the temperature is high and the pressure is extremely low. And the salinity, again, it's going to be nearly constant across all the depths, but salinity doesn't really play much of a picture when we talk about seawater. Uh, so as the temperature starts decreasing a bit, the speed of sound will keep on decreasing because temperature is a controlling factor here. Temperature is the more dominant factor. But then there'll come a depth in which we reach near to 0 degree in terms of temperature, like 2 degrees or 3 degrees. And that's when actually pressure kicks in. Now the pressure is increasing at this point, and pressure is a more dominating factor as compared to temperature. And then you'll see that the speed of sound again increases. So usually the kind of curve that we see in deep waters is essentially a kind of a decrease in sound speed followed by an increase in sound speed. Now, this will be of significance as we move forward. Now, there are three other factors for when we look at the acoustic propagation in water, which is the absorption, scattering, and reflection. Now, as again with any kind of signal, when the sound wave travel through water, they lose energy due to absorption, and that sound energy gets converted into heat. And this is basically a frequency dependent process. So higher frequency essentially means that more is absorbed quickly, and that is the reason why we see that it travels less distance. So higher frequency signal will travel less distance. Lower frequency, on the other hand, will essentially be allow us to travel more distances. Low frequency signal. Now, the interesting thing to note here is that the most of the anthropogenic noise that we have, the shipping noise and everything, it's a low frequency noise. And all the marine mammals that communicate, leave marine mammals, even the sonars, every kind of devices that we use to communicate, we use low frequency because we want the signal to transmit as much distance as possible. So again, we are creating a noise that is interfering with the signals that is being used for communication, both from a marine mammal perspective as well as our own devices that we are using. Now, again, as I said, sediment type of the waterbed also has an aspect. Depending upon the type of the sediment, the absorption coefficient of the sediment will change, and that will also have an impact. This thing. When the sound waves, so again, interference of just like every other signal, there will be scattering of the signal, the sound signal, that will weaken the sound wave. But this scattering per se will also actually produce its own echoes. Again, this again makes the underwater sound interpretation a bit of a challenge. Now, if we have sediment particles that are extended in the water column, that those sediment particles will themselves also cause scattering of sound wave, and then that will get reflected into multiple directions. So there are two challenges. So throughout this presentation, I'm going to note down a few challenges that we come across here, essentially hoping to try and point out towards what are the real world problems that we actually look at. Why is underwater communication is like, what are the actual challenges when we talk about underwater communication? So the first thing that we looked at is that the dynamic and real-time estimation of noise is a problem. Will we be with all these kind of factors taken into consideration, absorption, scattering, reflection, the speed of sound, is it even possible for us to estimate the transmission loss in real time? Can you actually predict, can you actually have an understanding of what is the type of sediment in a particular area, or can you have an understanding of how much amount of shipping noise is there in the region, how much amount of wind noise is there in the region? There are multiple factors like where shipping noise, wind noise, offshore oil, if there is an offshore oil rig that is drilling there, there's a noise that is generated by that. The huge amount of noise is coming from varied sources. So how much can you actually take into account? How will you actually come into, how will you actually create a software or an algorithm that will take into account everything and say that in real time, dynamically, I can give you a noise transmission loss that is happening in a given signal. And I'm talking about a real world thing, not something that we simulate per se. And second challenge that again we see is that, again, this is kind of a signal processing challenge, that, and this is something that has been there for quite a long time, essentially, that any and all signals have a lot of noise due to echoes, interference, etc. So how do we actually trim these out? How do we identify which noise are caused due to echoes and interference, and actually which part of the signal in itself is a noise? How do we trim this out? What are the different ways to trim these out? So just take a note of these challenges. We'll look at some form of solution for them as we move forward. Now, we spoke about how sound travels and how sound speed affects the signal traveling. Now, there are different zones that are being created in the water column based upon the speed of sound and other factors that are there. So these zones can actually have, yeah. So for example, there are three key layers that we look at. One is a surface mixed layer, a thermocline layer, and a deep isothermal layer when we look at any kind of a water column. What we mean by a surface mixed layer is that when, for example, if we take the Bay of Bengal or the Arabian Sea per se, so there is a high temperature in the surface. but then there's also constant waves or winds that basically cause these waves. Um, and what that means is that there is a mixing of layer that is happening. That temperature that we see, if there's a temperature of, let's say, 27 degrees that is established on the surface, that gets mixed with the bottom below a layer, let's say just 10 meters below the surface layer. So what we that creates is a surface mixed layer where the temperature and salinity is relatively uniform, and there's not much of a change. It's important to understand this because this again impacts how a signal will propagate. Then we also have something called as a thermocline layer, which is essentially what we see after the mixed layer, where there is a rapid decrease in the temperature as we keep going down, because again the deep ocean, there is no light that gets transmitted, the heat does not get transmitted, and therefore there is a decrease in temperature. And as I said, there is a decrease in temperature, the pressure will kick in, and due to that pressure there will be a sharp increase in the sound speed. That is what we call as the thermocline layer. And then we have a deep isothermal layer that is beyond that, wherein we say that now the temperature has decreased, and now it is also like stable. Now it's essentially falling down by, let's say, 1 degree or 2 degree at max. So that means the temperature is not really having any impact, and the sound speed again is kicking in because of the increased amount of pressure again. So that's essentially what we call as a deep isothermal layer. Again, it's important to note sound travels faster in the warmer water. Again, I think we discussed just now due to how temperature impacts the speed of sound. Um, so this is a representation. This is what I was talking about when I said how a speed of sound looks like when we talk about across a water column. So as you can see, initially there is a sharp decline in the speed of sound. This is because there's a decrease in temperature. And at a point of, let's say, 1,000 meter, 1,200 meter in this factor, pressure starts kicking in. This is where at 1,500 meter is where the temperature starts getting, there's hardly any decrease in temperature at this point, and therefore the pressure starts kicking in, and the pressure is being the more dominant factor. The sound speed now gets controlled by increase in pressure, and the speed of sound again increases. So yeah, this is the kind of curve that you normally see. Now this changes from region to region, but what this actually does is that it creates a different conditions for the propagation of sound. Now, before we move into the different kind of zones or channels that are being created by this speed of sound, it's important to reiterate on the Snell's law, which essentially states that the sound will travel at different speed at different layers of the ocean. And when the sound moves from one layer to another layer, the speed changes. So it bends due to the Snell's law. To summarize Snell's law, there are only two statements that we need to look at, which is that one, if the sound moves into a slower medium, so if you're looking from a high speed to a slower speed medium, it will bend towards the normal, and the other way around, if it moves from a slower medium to a faster medium, it will bend away from the normal. It will have an upward refraction or the upward bending of rays. So let's look at some of the ducts that are being formed. Now the ducts are basically essentially sound channels where if a signal is being propagated, it will essentially take that kind of a path because of the properties of the water, properties of the speed of sound that influences the sound signal. So the first one that we can look at is the shallow water duct. Shallow water duct is that, again, shallow water, there is not much of a depth as such. So the sound speed, as you can see, the speed of sound, the sound waves essentially bounce between the surface and the seabed. So there's not much of a depth. There will be huge of multipath propagation, and this will create a lot of reflections, complex scattering, propagation patterns, and yeah, I mean, you can see that the key fact to note here is that the sound does hit all the corners. There are no corners that the sound does not hit in, and therefore it is good for short range communication. So in most of the like in the coastal and harbor areas, we can see this kind of a duct being formed, where we can, obviously there are a lot of refractions, but at the end of the day, the signal does reach the end. The second layer that gets formed is a mixed layer duct. So again, I talked about how mixed layer is formed when a wind-driven mixing creates a nearly constant temperature layer. So because there is a constant temperature layer, the speed of sound will start increasing gradually at a certain point. What this creates is that it creates a kind of a shadow zone because sound waves bend away from the mixed layer and do not reach the certain depth. again, the Snell's law comes into picture, where if we are moving from a slower medium towards a normal, if we are moving from a slower medium to a faster medium, it will move away from the normal, and therefore it will go again, bend up, bend up, bend up, and so on. So what it will create is more of a mixed layer duct, and there will be some part, again, there are some signals that will not follow this duct. We'll talk about that, which is called as anti-waveguide propagation. But what this creates is something called as a shadow zone. Now, the two important things to note here is that most of the anti-submarine warfare, or the applications that we look at, anything that kind of tries to tackle. So if you want to create an application that wants to predict where a submarine can be placed in a given region, if you want to use machine learning algorithms for that, using this mixed layer duct is what you will ideally be looking for, because mixed layer duct will form a shadow zone. And there are two important reasons why mixed layer duct. One, because the depth is relatively manageable. Usually submarines cannot dive deeper than, let's say, even 1.52 kilometers of depth is extremely huge, because there's a huge amount of pressure there. The submarine will collapse in that kind of a pressure. So we usually want to look at a depth of 150, 200 meters, and so on. So that kind of a depth, in that kind of a depth, when you have a shadow zone, so if a submarine is placed here, you can be sure that the signals that are being transmitted from here cannot reach this shadow zone. And that's what this shadow zone is mostly used for in terms of anti-submarine warfare. The third kind of zone is a polar surface duct zone. Now, this is most popularly found in the polar regions, like, for example, Russia for that matter, where the surface water in itself is cold. So unlike the temperate regions that we have in India, where the surface is around 28 degrees, and so polar regions have a very less amount of a temperature at the surface itself. What that means is that the sound speeds start increasing very rapidly at a very low depth, as you can see here in the sound speed graph. And therefore, what that starts creating is a polar duct, and that polar duct is created here in this particular point, polar surface duct. This essentially, what it does is that so your sound waves are essentially trapped in the near the surface, because there's going to be a strong downward refraction. Again, the signals will start bending again towards the normal, that is up, due to Snell's law. And what benefit this means is that even at a low frequency, if you emit a signal, because of that polar surface duct, your signal will essentially transmit for a long range, and without much of a transmission loss, and therefore it is very effective for deep water communication in that sense. Again, unfortunately, this is something that we do not have. We'll talk about this in the next few slides. But polar surface duct, although extremely useful for, again, sonar communication, is not something that we can have because of the temperate region that we are in. Now, this is probably the deep sound channel, or the SOFAR channel, is probably the most ideal channel that gets formed. Now, at this particular point where my mouse is at, as you can see, again, this is a point where the temperature goes to absolute zero. So as you move up, the speed of sound increases. As you move down, the speed of sound increases. And we know that when we move from a slower to a faster medium, it will bend away from the normal. So it will keep bend away from the normal, away from the normal, away from the normal, away from the normal. So this kind of a deep sound channel gets generated. And what that means is that your signal, if transmitted from here, get transmitted to very long distances with least amount of transmission loss happening. And you can, if you emit a signal here for at least hundreds of kilometers, at least 100 kilometers without much of a transmission loss, the signal will have a impact on the other end for up to 100 kilometers. The last form is basically the convergence zone. So this is kind of a kind of a flip side, where the sound waves they get refracted downward, and then it starts bending and upwards due to the increasing pressure at depth. So when we cross this 2000 meters of depth and so on, there is a huge amount of increase in the sound speed. This will essentially create a convergence zone. And the focus, so this kind of a focusing effect will lead to alternate high intensity, low intensity kind of a zone. And there are certain specific points where the sound intensity will essentially strengthen, and those are what we call as a caustic point. Again, this is something that is very useful for long range sonar detection, based upon where we look at, what kind of a region we are looking at. Of course, at this, if we're looking at the temperate zones like such as Indian Ocean region, it's not possible for us to deploy submarines. However, other submersibles, AUVs, if possible, if deployed, can make use of these convergence zones. Yeah, we spoke about the underwater sound channels. I'm going to skip over this. Yeah, so it's important to note that again, this is probably not that very nicely visible, but between the polar regions and between the temperate regions, you can see there's a significant difference in the temperature that is being sound speed profile that is being generated, and that causes something called as this. Now, over the past few years, actually since the very inception of we've been buying sonars from Russia or most of the polar countries which actually create these sonars. These countries, for them, the sonar, so we basically we buy, let's say we purchase a sonar from Russia or any other kind of a polar country for that matter. The sonar works extremely well in their region, but then we bring it to our region and we can see a significant drop in the performance of sonar. Now, that is not because of, that has nothing to do with the sonar that has been built. It has more to do with the environment in which we are actually deploying that particular sonar. In polar regions where the temperature is extremely low, the kind of a SOFAR channel that we see here, or what we saw of the surface struck channel, that gets created at a very low depth, and that means you can deploy a submarine at, let's say, 250 meters of depth, and you can get that kind of an efficiency in your sonar. However, for Indian Ocean region, our SOFAR channel gets created. Again, this is here, 1,500 meters is where our SOFAR channel gets created in Indian Ocean, and 1,500 meters is not a region that can actually be achieved. I mean, the depth is not something that you can deploy very easily to. Again, as I said, due to massive amount of pressure, your equipment needs to be able to withhold and withstand that kind of a pressure. And therefore, we are not able to take advantage of the SOFAR channel that is being generated. And so the sonar range for temperate regions is lower than the polar regions. Again, that's one more challenge that we have here. So so there's one last concept that we need to cover, which is called as anti-waveguide propagation. Now, this is something. What it means is it's a unique form of sound propagation in the ocean, where the sound waves reflect away from a central axis rather than bending. So we saw that duct where the sound gets trapped. So this is the kind of anti-waveguide propagation where the sound waves will essentially go out of this duct, and it will then because it will never return back, so that signal is lost. And there's a huge amount of signal attenuation and everything, so that signal is not something that we can actually use anywhere. Now, this is different from a typical waveguide that we have, such as the SOFAR channel, where the sound bend towards the central axis and they get trapped in that thing. This is something where we cannot let it guide over the long distances because of the fact that it gets away from that duct that is being generated. So if I want to show you again with an example, we can look at this one here again. If you look at the third one, which is the polar surface duct, we can see a possible anti-waveguide behavior here, where the sound speed, when the sound speed decreases with depth, which is like in the top half of this one, there is an upward refraction that is being caused. But then you can also see that the sound waves are actually escaping towards the surface, and there's a deep traveling sound wave, and these which are escaping the duct will not return back, and therefore these signals are lost. So again, this is one example of how anti-waveguide propagation actually works. Yeah, so as we saw, again, in that example, previous example, sound speed was steadily increasing with depth, and therefore the continuous downward refraction was happening, and therefore there's a signal loss. All right. Again, as we saw, propagation of sound in shallow water is something that is that has a lot of aspects to cover, which includes multipath propagation, high attenuation, scattering, and diffraction. All of these things happen because of the fact that it's a small depth, so multiple reflections they create the overlapping path. There is a rapid amount of absorption of acoustic energy. This again is because it's a shallow water, that means that there's a huge amount of attenuation that happens due to the type of sediment and the mud rocks that are present in the region, and so on and so forth. And of course, there's a lot of scattering and diffraction because, again, the sea flows are always irregular. and therefore the propagation is never going to be a coherent propagation. Right. So moving to the next part of the whole presentation, this one essentially is no signal transmission. The environmental factors that affect the signal transmission is not the only challenge that we look at. The biggest challenge that we look at, the ambient noise level in the region. There are a lot of factors that influence it. Now, a reduced, if we have a huge amount of ambient noise, that essentially means that we have a reduced signal to noise ratio. We have signal masking, which means that if you have a ship propeller or industrial activity, as I said, if that is happening, it is very difficult for a submarine using a passive sonar to actually detect an approaching vessel because there's a huge amount of noise in the region. There's a lot of multipath distortion that happens. Frequency dependent attenuation, high frequency signals will suffer more attenuation in noisy environment than the low frequency signal. So for example, if a whale is trying to communicate on a low frequency, it will try to travel farther than the high frequency dolphin echolocation that is happening. And therefore, depending upon the kind of a frequency, the different kind of attenuation will happen to your signal. Uh, Again, we can't go too deep into the Doppler shift aspect, but depending upon the speed of the depending on the speed of sound of a particular region, noise that is present in high speed environment. So, for example, if there's a fast moving vessel and things like that, it will introduce a Doppler shift, which will basically alter the receiving frequency, and therefore it will mislead the sonar that is tracking the acoustic communication. So when we talk about anthropogenic noise, anthropogenic essentially means a human-made noise. Any kind of human activities that create noise, like shipping, construction, military exercises, energy exploration, so oil rig, mining, and all those kind of things. All of that creates a huge amount of noise, and that noise will essentially disrupt any and all kinds of marine life that is present in the region. As I said, marine uses sound for communication, and that means that noise that is being generated will interfere with their communication. It will give them stress, physical harm. And we've also seen a lot of whale strandings because whales cannot communicate. If there's a huge amount of noise in the regions, whales will not be able to communicate, find their prey, find food. And as a result of which, they will get lost, they will get away from the pack. And we've seen a lot of examples where whales have stranded on the coasts of Goa or Mumbai and so on. So that all of that is because of increased noise in the region. Anthropogenic noise can be acute or chronic, high intensity and short in duration, or low intensity and traveling the long distances. There are both natural and anthropogenic, which creates a lot of noise. However, anthropogenic is the one thing that we can actually manage, do something about, and therefore we essentially try to focus on that. And plus, natural noise doesn't really create that much amount of interference as much as anthropogenic. In the interest of time, let me quickly go through stuff. Now, when we talk about sources of anthropogenic noise, shipping is one of the biggest source of anthropogenic noise. As we can see, this graph essentially showcases that an oil tanker or a cargo creates a noise at 180 decibel and so on, which in comparison to a fishing vessel, which is smaller in length, will have a slightly lower amount of noise level. This map is what we had generated for one of our research work. These black dots that you can see are essentially vessels, and the regions, the color coded regions, reflect the noise level in those particular regions due to the marine vessel traffic that is present in the region. Right. Yeah, I'm going to skip a few slides. Right. Other such kind of things: seismic surveys, sonar operations, offshore construction and drilling, pile driving. So when you do a lot of drilling, there's a huge amount of noise that is being generated into the ocean, and all of those aspects that they create a huge amount of noise. Sediment transportation also creates a noise. It's an active contributor to the URN, and they generate the frequency in the bandwidth of low to mid frequency level. So sand, gravel, and pebbles, when they move along the seabed through the process, due to that rolling and everything, they create a lot of noise in the region. An interesting aspect to show is this one, where you can see that the noise sources, as you can see, what we are generating is basically overlapping with the noise, or overlapping with the bandwidth that the marine mammals use to communicate, and therefore any kind of noise that we generate, it's directly impeding their ability to communicate, find prey, and so on and so forth. there are a lot of URN reduction approaches that have been provided by IMO. The idea is that you perform modifications to your hull, you take operational measures such as reduce the ship trim optimization and route planning to avoid sensitive marine habitats. Um, now, one thing that everyone is talking about is how we can increase or how we can decrease the noise level. But to be honest, it's not something that, like, if you are a stakeholder, if you are, let's say, a shipbuilder, you wouldn't actually care about what the amount of noise you're being generating. If that means that if slow steaming basically means that if you want to reduce the speed of ship, if that basically means that you will reach your destination late, you're not going to really worry too much about the noise that is being generated in the ocean. You're going to go on in full speed. You're not going to take that into consideration. So therefore, a lot of these policies that we kind of showcase, we also actually look at how we can create a win-win situation, which is extremely important. So if you want to create a policy, you want to make sure that how the stakeholder is going to win in that situation. So for example, if you are talking about cavitation reduction, or like adding some kind of adjustments to the cavity propellers so that the noise being generated is less, how to basically make them steam their, like, slow steaming is essentially like driving your vehicle in economy speed. If you keep driving in the speed of 40, and it will create a less amount of noise. But then what we promote essentially is that that will also increase the fuel efficiency of your vessel. So it's kind of creating a win-win situation. You're reducing the cost and you're reducing the noise level that is there in the region. So that's the kind of incentives that are being provided, or that's how we push the policy of slow steaming and everything. So yeah, so as you can see, just to summarize everything, managing URN is a difficult task. There is a variable sound propagation. The ocean conditions are dynamic. The noise sources are diverse, and there is a lot of financial constraints that we need to look at. So how do we go about solving these challenges? So two last slides to quickly show some examples here. So again, dynamic real-time estimation of noise is a problem. We looked at that thing, how can we actually estimate the transmission loss. So we recently published a paper. You can go ahead and read this paper. What we did was we actually constructed a neural network that instead of calculating the transmission loss, that will go ahead and predict the transmission loss in the region. So we have created a neural network that is trained for the region of our A, B, and C. So given a source and a receiver, it will automatically predict the transmission loss that's happened, because the neural network has already been trained with the environmental conditions of the region and so on and so forth. So therefore, the chunk of the work. So for example, if you have 10,000 sender receiver pairs, so when I say sender receiver, I mean ships. So if you have 10,000 ships and you want to calculate the noise that is being generated by those 10,000, 20,000 ships, you're looking at an O of n kind of a problem to solve, where you have a linear equation. You run those equations for each of the 10,000 ships. What neural network will do is that it will drop it down to an O of log n kind of a problem, where it will exponentially reduce the amount of time it takes to perform the same kind of computation. The other such kind of a thing is essentially that in the there was a huge presence of orca whales in the Vancouver region, and what Google did was that they created a convolutional neural network, which essentially looks at which is basically trained on the image spectrum, power spectrum density. As you can see here, it is trained on the image for that, and it will perform image classification. It will see what part of the signal essentially is looking like a wind noise, which is looking as a fish call, which is looking at like a ship noise, and so on. And it will identify if there is an Antarctic blue whale. So this one is specifically for saving the Antarctic blue whale chorus thing, which is orca whales. And therefore it will identify if there is a orca whale in the recording. And if there is a record, if there is one, it will send a communication to the ship that you need to slow down or you need to take a different path. And that will essentially mean that we do not create a noise constrained environment where the whales cannot communicate. All right, with that, I sum up my 50 minutes, and I hand over to Jyoti ma'am.
Thank you very much, sir. It's my pleasure to express my sincere gratitude towards you. We would like to express our sincere appreciation for your captivating session on underwater acoustic communication at our faculty development program on next gen communication. Your in-depth knowledge and expertise in this niche area were evident throughout your presentation. You not only enlightened us the fundamentals, but also share the valuable insight into the latest advancement as well as the challenges in underwater acoustic communication. So once again, thank you for sharing your time and expertise with us. Your contributions has enriched our understanding of next generation communication technologies. So there is a one request to all the participant also. Sir is with us. Now I have to welcome next resource person, Dr. Jyoti Rangole ma'am. Let me introduce first. He, she completed his PhD in underwater signal processing in the year 2020 from SDGS Nanded. She has over 20 years of experience in teaching, research, and academic leaderships. His research interest includes underwater acoustic signal and image processing, where she has developed the techniques for analyzing underwater acoustic signals and imagery. His research area includes biomedical image processing, automation in agriculture and sericulture industries, as well as his research interests also include the product development field, where he designed and implemented engineering solutions for real world problems. He also contributed in the research publication. He published several papers in prestigious journals like Wiley, Springer, CSIR Journal, and Institute of Engineers. His research project includes automatic bird detection and cutting machines, where she has received funding under Yukti Scheme 2021-22 by the Ministry of Education, Government of India. His research project includes side scan sonar image analysis, where she got funded by SBPU, BCOD Pune, as well as for automatic counting of silkworm eggs. She has received the funding from SBPU, BCOD Pune. His work is although in the field of patent, so the patent on multipurpose egg hatcher machines also granted on his name, and another patent design of automatic sugarcane cutter with bud detection, it is under the examination. She has developed the product multipurpose egg hatcher machines as well as automatic sugarcane bud detection and cutting machines and automatic sanitization systems. In the field of entrepreneurships and startup, she working as a director at Web Electroline Private Limited, where she fostering innovations in technology driven solutions. So with this, I welcome our next resource person, Dr. Jyoti ma'am. Over to you, ma'am.
Hello, am I audible? Hello.
Yes, ma'am.
Okay. Whether my screen is visible?
Yes, ma'am. Your screen is also visible.
Yeah. Thank you, sir, for the introduction, and I'm thankful to Mr. Shridhar for building the background so that I can navigate ahead in the field of underwater communication. So let me dig into the history and evolution of underwater communication. So talking about the underwater communication, the journey started way back in 1914 to 1918, where the first underwater hydrophone was invented. So what is a hydrophone? It is same as a microphone. It's the same as mic in underwater. So this was invented by Lewis Richardson and Alexander. So this was just, they received a patent in 1912 itself, which was just a case after sinking of Titanic. So if you see the journey from World War I to World War II, and now we are in 21st century where we are looking forward for the modern and advanced underwater communication. As Shridhar has rightly pointed that nowadays we are using machine learning, artificial intelligence to solve the problems in underwater domain. So what modern innovations demands? So modern innovations in underwater demands integration of machine learning, artificial intelligence techniques, and where we can solve the problems like seafloor mapping. We can identify which are the enemy vessels, whether there are submarines in the sea or not. Then the modern innovation also demands hybrid systems. So like Shridhar has pointed out various ways, like we can have optical communication, we can have acoustic communication, we can have RF communication also underwater. So based on application, we can have a hybrid system which will serve our purpose, or which can solve a problem that we have undertaken. Then the third category where the modern innovations is expected is miniaturization of the devices. Since these devices are underwater, we need to look forward for the power consumed by the devices. Power optimization and size optimization is one more concern that one needs to address. So talking about the applications, it covers wide varieties of applications, military uses, civilian applications, and environmental monitoring. In military application, as I already told you, that we can have underwater surveillance in the sea, in the river as well. We can have a technique for detection of enemy vessels. We can have the techniques for detecting the buried parts or buried objects underwater. And we can have the diver communications. Talking about the civil applications, in civil application, when we have to go for underwater construction, it is mandatory to have a look at what type of sediment is there.
Sorry to interrupt you, ma'am.
Hello?
Sorry
Yes.
to interrupt you. Your slides are not moving, ma'am. Please check.
Now?
Your slides are not moving.
I'm changing the slides, sir. Should I reshare? Is it visible now?
Yeah, it's visible, but your slides are not moving.
Ma'am, you might
we are getting only first slide.
Yes, Shridhar?
Ma'am, you might want to share the whole screen instead of just the application of PowerPoint. It is just stuck at the first slide.
Acha, entire screen, no?
Yeah.
Now?
Yes.
Yeah,
Now
it works now.
Okay, fine.
Yes, okay.
Okay, let me go back. So we were talking about the applications, and in civilian applications, we should look forward for what is the sediment type underwater, so that it will be helpful for underwater construction. Then oil and gas leakage we can detect. For the rescue applications also, we can go for underwater communication. Now, talking about the environmental monitoring. So as Shridhar has rightly pointed, whatever is the underwater noise that we have to monitor, so we need to set such systems which will monitor the underwater noise. We can also analyze the marine life, that is aquatic life underwater. Then we can also monitor the temperature, pressure, and salinity underwater. And we can also have a geological activity for environmental monitoring. So, what are the technological advancements we are currently looking at? So, talking about underwater communication, we have currently innovations in acoustic modems, optical communication, underwater wireless networks. This field is dramatically increasing. But what is the challenge? Even though we have a drastic increase in the technological advancements in the underwater field, it comes with some challenges. So the challenges rightly pointed by Shridhar, that when we go for underwater, either sea or fresh water, the acoustic signal that we are dominantly using for underwater application, it suffers from signal attenuation, interference, and in this case, we have to ensure reliable communication when the water conditions are turbid. Like when you go with the sea water, you have higher salinity, like 35 parts per thousand is the salinity. So in that salinity environment or in the turbid environment, how well my communication system is working or how well my algorithms are working, that we need to ensure. So these are the challenges when we go for underwater communication. So let's once again have a look at what are the advantages of acoustic communication and what are the limitations and benefits. So here, as we know that acoustic is a term that is used for the sound. So we are using sound signals to propagate underwater, and we can use varieties of frequencies there. Like when you use low frequencies, the sound signals can travel a long distance. But when we use the higher frequency signals, those higher frequency signals suffers higher absorption. So you have a choice based on application whether you need to go with on what thing you have to compromise. Like whether you want higher resolution, then we have to select for the higher frequency signals. And when we want to travel a long distance, obviously you have to go with low frequency selection for the acoustic signals. Then next is what are the benefits and limitation. So even though the acoustic communication is suffers from slower data rates, but we can have long range of transmission. So that is a benefit, and benefit as well as limitation, both are highlighted here. Now talking about the sonar systems. So sonar stands for sound navigation and ranging system. There are two types of sonars available commercially in the market. One is passive sonar and other is active sonar. So passive sonars are used only for data collection, like they are only in listen only mode. They will listen only. They will not send any signal, and they will not they are not able to send any signal, but they will listen only. So when we have to go for monitoring the anthropogenic noise, we can utilize the passive sonars, or whenever we want to detect whether the dolphins are there in that region or whales are there in that region, then we can go for passive sonars. But when there is an application that I want to detect the object which is underwater, or when I want to detect what sort of sediment is there underwater, then in that case we have to go with passive active sonars only. So in active sonars, we will be having a transmitter that is called as a projector, and we will be also having a receiver part. So we will be having a hydrophone. So transmitter we will term as a projector, and receiver we will term as a hydrophone. So here you can see a picture here where the parameters of the sonars are also highlighted. So source level, then the target strength is given. So acoustic signal will be sent by the transmitter. So it will travel along the water column. during the travel, the signal will suffer from attenuation, absorption. So those losses we need to consider. And whenever it will hit the target, just for sample, I have shown a submarine here. So whenever it will hit the target, based on the target strength, a reflected signal, to which we call that as a backscatter signal, will be received back by the receiver section of active sonars. So here, in order to calculate the echo level at the receiver, formula we have mentioned. So echo level is given by source level minus 2 times transmission loss, because the signal is passing towards the object and it is getting back to the source. So that's why the transmission loss will be double. So it is minus 2 times transmission loss plus the target strength. So based on what is the target, like if you are going for seafloor mapping, you can have sand, you can have silt, you can have clay at the bottom. So based on, or you can have a buried object there. So what is the strength of that object? What is the reflectivity of that object? We will get the target strength. So the transmission loss contains 2 parameters. One is called as a spreading loss and other is called as a absorption. So spreading loss, there are 2 types. One is a spherical spreading, another is a cylindrical spreading. It depends on at what distance your object is. And this alpha indicates the absorption coefficient. So 2 nice models have been given in the literature. One is a Thorpe's model, another is a Franco's Garrison model, which will tell you how much is the absorption. So it is mentioned in dBs per kilometer. So this is how we can calculate the transmission loss. In short, I have tried to represent what is a backscatter. What is a term backscatter? So here the third term comes into picture, that is target strength. So target strength is calculated by the backscatter at an angle theta plus 10 times log of the area n-sonified. So AF stands for the area n-sonified by your sonar. I will highlight it in my next slides. So what is backscatter? So whenever a sound signal travels in water, at the time of reflection, there are 2 things, that the sound signals will get scattered in random direction, and other thing is that other part which is shown here, some part of that energy will be reflected back to the source. So this part is called as a backscattering signal. So based on the backscattering signal, or backscattering signal is a parameter based on which you can check what object or what type of sediment is there underwater. So I have highlighted here 3 types of sonars that are commercially available in market. One is called as single beam echo sounder, other is multi-beam echo sounder, and third is side scan sonar. So you can see, as the name suggests, single beam echo sounder will send only a single pulse and it will have a single beam. The footprint covered by that particular beam depends on what is the beam width. Next is we have a multi-beam echo sounder. So multi-beam will have multiple beams which will cover more portion of the seabed or the river bed if you are talking. So it will have a more swath width as compared to your single beam echo sounder, and all these will give you the one signal. Single beam echo sounder, multi-beam echo sounder, they will give you 1D signal. But if I want to at all map what type of sediment is there underwater, surface sediment, then you can have a acoustic image. So here you can see, here there is an acoustic image that has been shown. So how an acoustic image is formed? Your side scan sonar will send the acoustic signals. Those signals will get hit with the surface of the sea floor or river floor. Then it will get reflected back to the sonar, where the sound pressure. So the sonars will emit sound signals. So that sound pressure will be converted to a electrical voltage value, and that electrical voltage value is given a gray level. In this way, we can convert a signal into an image. So by using the side scan sonar, we can get an acoustic image of the surface sediment. I will show you some samples there. Once again, I have tried to show the same thing. This is my single beam echo sounder. Talking about the application of single beam echo sounder, they are particularly used for calculating the depth of your reservoir or calculating the depth of your sea. And in a limited way, they can be used for sediment classification or seafloor classification, as it doesn't cover much of the portion of the sediment or much of the portion of the seafloor. It has some limitations. So many of the people, they use multi-beam echo sounder. So multi-beam echo sounder, you can see here that it covers maximum portion, means how many beams you have. Based on that, it will decide how much area it will cover of your seabed or the river bed. So this is about single beam and multi-beam. Now, I have tried to show a sample signal here that have been collected by using single beam echo sounder. So where you can see we have three parameters that have been shown. One is ping number. Ping number is nothing but whenever you send a sound pulse, that is called as a ping. So you can have multiple pings that you are sending one after the other. I'm talking about single beam echo sounder here. So take ping number 20. So when I send a ping, the signal will be reflected back from the sea floor. I'm talking about the sea floor now, and you will get a reflected in this way. So what are the parameters that I will get here? I will get the time and I will get the amplitude. So I don't get the information about the frequency contents of the signal. So we can utilize various signal processing techniques, like you can apply wavelet transform or DTFT in order to calculate what are the frequency contents in this signal. So if you send say 100 pings, you will get 100 such echo signals. So based on these 100 echo signals, you can calculate, you can have a mechanism that you can, instead of processing all the 100 signals, you can bunch them together based on the correlation between the signals, and you can have an average signal or you can have an ensemble average, and you will get a single echo signal. So the same thing has been shown here, but it is a raster plot. The same parameters, you have the ping number, you have the time, and you can see here the amplitude. So this has been captured at 12 kilohertz frequency. MZ indicates what is the grain size. So whenever you talk about sediment, it can be silt, it can be clay, it can be stone. So MZ will indicate what type of sediment it is. So it is a mean grain size, which has been measured in millimeters, diameter in millimeters. So moving ahead, already Shridhar has covered the salinity and temperature. Temperature plays an important role because sound speed in underwater is directly proportional to temperature, pressure, and salinity. But for 1 degree change in temperature, the sound speed changes by 4 meters per second. While for one parts per thousand change in salinity, it changes by only 1.4 meters per second. And the pressure per 100 meters, it changes by 1.7 meters per second. So the dominating factor, if you consider, that is a temperature. And when you go for the sea, salinity will also play an important role. And when you go deeper in the sea, pressure will be a dominating factor. So turbidity also has been discussed by Shridhar. I will not invest the time. I will just move ahead. This part also has been elaborated. So here, this is the temperature profile along the water column. So the depth has been shown and the temperature has been shown here. So here we will focus much on this thermocline. So what is this thermocline? As the depth here is increasing, the temperature value is reducing. But after a point, even the depth is increasing, the temperature remains constant. So this is called as a sound axis. This is called as sound axis. This is about the temperature profile. Then sound speed already discussed. So this is a thermocline region, and here this is a sound channel, or this is a sound axis, after which your pressure becomes dominant and the sound speed increases not due to temperature, but it increases because of the pressure factor. Pressure becomes dominant there. So now particularly I'm addressing a case study which is targeting to the fresh water. So we know that our country comes under a tropical region. So what is there are regions which are tropical, temperate, semi-tropical. So what is a tropical region? So tropical region is characterized by seasonal and diurnal variations in the temperature. So we can feel that the temperature is seasonally varying, as well as during a day also we can experience what is a change in the temperature. So we are in the tropical Pune region particularly I am talking about. So the Pune region, we come under a tropical region. So what we have targeted, we had targeted that to study the acoustic behavior in fresh waters. Particularly, we have targeted the lake systems or reservoir systems. So, very first thing, when you do the acoustic experiment, you have to first of all study the environmental conditions at that site, because sonar systems are highly dependent on the performance of the sonar system is highly dependent on what are the environmental conditions at the field or at the site where you are working. So temperature, you need to analyze temperature, salinity and pressure parameters at the environmental site, and you have to calculate the sound speed profile. Very first thing you have to do is do the sound speed profile analysis of the given site or of a selected site, right? So in the literature, there are two ways to calculate the sound speed profile. One is a CTD based method. CTD stands for conductivity, temperature and depth, which is particularly based on temperature, salinity and pressure. And other is time of flight based method. So here we have targeted CTD based method for calculating the sound speed. So if you see the literature of either the sea water or a fresh water, you will find many empirical formulas that are based on CTD. So conductivity, temperature and depth. On that factor, they have designed many equations, many what you can say, many multi-polynomial polynomial degrees equations they have designed. So we have picked up all those, Wilson, then Leroy, many authors are there. So this table shows you at what temperature range you can utilize those equations, at what salinity and at what pressure, because these will be working in a particular limits, right? So if you see the first equation, it has 23 terms to calculate. If I have to at all calculate the sound speed, now I have to do the calculation of 23 terms, so that for a given temperature, salinity and pressure, I can calculate the value of sound speed. So all those things are listed here. So since we are working in the fresh water, I have limited my scope for freshwater lakes, not even to the rivers, for the freshwater lakes. So when you say about the freshwater, here I have listed the lake types, what is the conductivity and what is the salinity. When you go for the freshwater, the salinity is about 0.5. Typical value is 0.5 parts per thousand. So for very fresh water, the salinity is very less. When you go for the sea water, it touches to 35 parts per thousand, right? So so now I will highlight a real case study that we have undertaken at Khadakwasla Lake. So my PhD was on the same, the characterization of tropical freshwater lake systems. So what in the further presentation, I will be listing study of freshwater environment. Then what is the sound speed? We have designed a computationally efficient sound speed model, and how is the channel underwater channel impulse response for the freshwater particularly, and what type of sediments are there in Khadakwasla Lake. So my presentation will move ahead with a wake-up call on the reservoir siltation. So as we know that India suffers from Indian rivers particularly suffers from heavy deposition of sediments, and as the sediment deposition goes on increasing, the life storage of the reservoir goes down. So the Indian government is facing a severe problem of sediment deposition, and because of that there is a huge scarcity of fresh water. So this is the alarming situation for all of us, that siltation is going on day by day. The literature suggests that 1% water storage capacity of the globe reservoirs we are wasting annually. So you can imagine that 1% we are losing, 1% capacity we are losing every year. So I have put some facts and figures here. So many articles were there in Times of India that which addresses that we are losing of the life storage capacity of fresh water. So if we talk about our local condition, in the Pune region, we have Khadakwasla Lake. So at the time of building the Khadakwasla Lake, its capacity was 40 TCM, and now its capacity is 1.75 TCM. So you can imagine that half of the capacity of that lake we have wasted, and government is putting efforts to remove the sediments. So for that purpose, underwater sonars can be active sonars can be particularly utilized to know what sort of sediments are there, because government is giving huge contracts and means huge sum government is investing on dredging activities, but whatever are the systematic measures that the government needs to take, those are taken in a limited states. So here there was one article that Maharashtra government has decided that they will start removing the silt from 31459 across the state. So this was an article in 2017, and Maharashtra government has already started taking the steps in that direction. But how the acoustic techniques will help to understand the sediment class before dredging activities, the sediment classification needs to be done, and based on that, whatever investment is done to deploy the dredgers, that has to be systematically planned. So what we have done at for the Khadakwasla Lake, our objective was to analyze the freshwater channel, the sound speed profile at the freshwater channel, the channel impulse response, how is the statistical behavior of how is the PDF probability distribution function, density function of the underwater channel at Khadakwasla Lake, and what type of sediments are there in Khadakwasla. That was our objective. We have conducted this experiment in 2017 for complete 2 days. We have deployed 3 sonars underwater, and thanks to my guide, Dr. Commander Arnab Das, because of him only, because when you plan such an experiment, you need huge support, financial support, as well as all the government official formalities you have to complete. So I'm very much thankful to Maritime Research Center. Because of their support only, I could progress further in my research work. So if you see here, I have highlighted Khadakwasla Lake on a global map. So the length of the lake is around 22 kilometers. The width is maximum up to 1 kilometers. And as I told you, the storage capacity is currently, when we did the experiment, the current capacity, storage capacity was 1.75 TCM. So this lake particularly represents a tropical freshwater lake. So why we have selected this lake? It was not the case that it was near to us. That's why we have not selected. We have selected this lake because it represents a tropical environment where you can see the seasonal and diurnal variations in the temperature, and those variations we can capture and we can apply those corrections in our algorithm. So when I started my research, there was at all nothing was there in the open source domain where I can capture the temperature, from where I can capture the salinity, because limited studies, CWPRS have done the study at Khadakwasla Lake, but they were not having the data set available readily. So I was not having any alternative than conducting this particular experiment. So I will show you here the profile of the temperature from Jan to December. How is the surface temperature of water and how is the bottom temperature? So what we did, we deployed 3 sonars as I mentioned earlier. The first sonar was single beam echo sounder that we have utilized it for calculating the speed of sound underwater. Then we have the CTT meter. We have collected CTT parameters. Here you can see the experimental setup. Here this is the side scan sonar, which will give us the sediment layer image, acoustic image. This is the CTD sensor. This is the top unit of the side scan sonar, and we were having some technicians which were available with us. We have worked with Fugro, which is a well-known company in Mumbai, who are particularly involved in acoustic experiments. Their expert team was with us, and we had deployed the sonars at 5 to 6 different places, and we have captured the CTD data. So I have highlighted the locations also, the date also, the time also, because we need to capture the temperature and salinity and the pressure at particular time instance. So here I have shown the same parameters in a box plot. Here, this is the real experiment results, that how was the temperature variation. So the temperature variation was from 24 point about 24 to 27 during that day. On a day that we have planned experiment, we had planned that experiment in October month, so that in October we can have maximum variations in the temperature. So the salinity that we captured, the salinity, we found that the lake is very fresh, so fresh water. So we found the salinity in the range from 0.044 ppt to 0.05. So after this, all the models that I mentioned earlier, Wilson, Cook, and Leroy, Melvin, so we have calculated the sound speed profile. So whatever thing we saw in theoretical figures, the same we could replicate here in the practical. So these are the results from Khadakwasla Lake for the sound speed profile. Then we deployed the third sonar, that is called as a sub-bottom profiler. So what is sub-bottom profiler? So I will take you to the next slide. So here, whatever white portion is there, where I am moving the mouse, it is a water column, and this is the sea floor. This is the what you can say, river floor, sea floor, whatever it is. So, and this is the sediment layer. I think I'm very much clear to you. So this is the sediment floor. So what a sub-bottom profiler will do, the sub-bottom profiler will give you the stratigraphy of a sediment column. Means along the sediment column, if I have say 15 meters of sediment column layer, then within that 15 meter sediment column layer, how is the layer 1 is what is the morphology? In short, what is the morphology? What first layer is, whether it is mud, silt, sand, what is the second layer morphology. So you can see it only by utilizing the sub-bottom profiler. So what is the ultimate aim of utilizing the sub-bottom profiler is it will penetrate into the deep sediment layer, and along the sediment column, how is the stratigraphy of the sediment? What is the class of sediment that you can analyze? And it is very important when we do any sort of underwater construction, because before doing any underwater construction or before laying even underwater lines, cables, we have to do the analysis of the stratigraphy of the sediment. So we have deployed that also. For the sub-bottom profiler, once again you have transmitter. It is also active sonar. You have transmitter, you have receiver. So when you transmit the acoustic signal, it will get some part will get reflected from the first interface, then it will get deep into the sediment layer. Then once again you can catch the reflected signal. In this way, we have three layers that have been shown. Interface 1 is your water layer. Then interface 2 is one category of sediment in the same way, right? So I will show you a sample signal that we have acquired of sub-bottom profiler. So you can see these are the signals that we have captured. Here, these are the reflected signals from the sub-bottom profiler. So you can analyze this signal in parts, like the pulse duration that we have transmitted. We have transmitted an acoustic pulse for 10 millisecond duration. So you can analyze the reflected signal in 10 milliseconds duration. So how is the behavior? From that 10 millisecond duration, you can analyze what is the energy of that signal, and from that energy, we can map that energy to the reflection coefficient of the sediment. So we have utilized the model-based technique where the signal, we will calculate the energy of the signal and we will map that energy to a well-known model that is there in underwater, that is called as a Hamilton model. So the Hamilton model will give me the reflection coefficients from the energy. So these are the sample signals. The next one was side scan sonar. As I told you, it will give you the image of the sediment surface. It will not go deep into the sediment layer. It will give you only for the sediment surface. So it operates in high range, that is dual frequency. 400 kilohertz is the lower frequency, and high frequency is 900 kilohertz. With 400 kilohertz, you can have a crude view, and with 900 kilohertz, you can have a detailed view of the sediment samples. See here, these are the sample images that we have collected. This is the sediment surface of Khadakwasla Lake. So Khadakwasla Lake. So here, the image is formed by that side scan sonar. Whatever dark portion is there, so it indicates that these are the sediments with very high reflectivity. And if you see this covers the sediment which are having low reflectivity, like clay and mud. Here you can consider this as sand, or might be stones, might be also there. So this is how we have captured the data. After that, we have worked on designing the efficient model for sound speed, particularly for the freshwater. So we have designed two models. One is simple linear regression, multiple linear regression model, and other was multivariate polynomial regression model. So we have also done the statistical performance analysis of the models that we have developed. So I will show you the equation that we have derived. So this is the equation that we have designed for, we have modeled it for calculating the sound speed at freshwater lake with the inputs as salinity, pressure, and temperature. So this was a simple model that we have formed here. Then after that, we have also formed a polynomial regression model, and how well these, whatever model we have proposed, how well it fits to the data. For that purpose, we have done some statistical measures. So all the coefficients that we have calculated, that our model is giving, it fits to the real data with 95% of confidence. And when we go with the regression analysis or regression problem, in that you should also ensure that your model is not overfitting the data. So for that purpose, we have also done the analysis where we have calculated the p-value of the regression coefficients, and we have done the hypothesis testing. The p-value we found was 0.001. So this p-value is much less than the alpha value, that is at 95% confidence level that we are calculating. So we rejected the hypothesis that our null hypothesis was all the coefficients are 0 or they are insignificant. Whatever model we have designed, we have tested against this null hypothesis that all the coefficients are insignificant. But whatever model we have designed, it has rejected this null hypothesis. It states that the coefficients are really significant. So here I will just move ahead. So this figure you can see for sound speed profile with temperature and pressure, and we have kept the salinity constant. For the freshwater lake, we have considered that to be 0.05 parts per thousand, and we have plotted this 3D plot. So this is with a standard model that is called as Chen-Miller's model, which is very renowned model that has been used in freshwater as well as seawater. So what we have done, we have compared the performance of our model with this Chen-Miller's model. So here is our linear regression plot, and here is the plot for the model that we have designed with polynomial regression. So how well our model fits to check how well our model is near to the Chen-Miller's model. For that purpose, we have plotted all these graphs together, and whatever model we have designed, the R-square value of that, so it is called as coefficient of determination. It is to a value 0.97, and the root mean square error between our model and the standard Chen-Miller's model. I am talking about polynomial regression model. So it is 0.5 meters per second. But since we have collected only the limited samples from the Khadakwasla lake, we have also done the validation that this much data we were not having, because hardly we have conducted the experiment for 2 days and we have collected only 200 CTD samples. But it is difficult. These 200 CTD samples won't cover the entire temperature range or entire pressure range of the Khadakwasla lake. So for that purpose, we did the validity of our model for the temperature range from 10 degrees Celsius to 40 degrees Celsius, and the depth or the pressure, we have considered the depth up to 15 meters. So for these conditions, our model was working very fine, and it was giving the RMS value of 0.5 meters per second. So our next target was to calculate the channel impulse response. So as we know, the underwater channel impulse response is what you can say, it is very random, and it is very site specific, that the channel impulse response of sea might be different than any other sea where you do the experiment, right? So you might be aware of the fact that there exist many channel models for the RF wireless communication, and there are very renowned channel models like rice distribution, railing distribution, which are very popular for the RF communication. But when we talk about the underwater communication will never rely on a single statistical model. So many of the authors reported many distributions. Like some authors reported that at their site they found that the impulse response is following the Ricean distribution. Some reported that they found reported K distribution. And what we did, how is the channel impulse response at the freshwater lake Khadakwatla? For that purpose, we did the channel impulse response analysis. So the channel impulse response analysis, you know that here we have the transmitter, we have the receiver. The receiver will receive the signal from n number of paths, like from the direct path. It can receive the signal from bouncing to the surface, bouncing to the bottom, or it can have multiple bounces to the surface and bottom. This is the very severe problem when you go with the shallow waters, because the depth is very less, so your acoustic signal can have multiple strikes at the surface as well as at the bottom. So your signal arriving at the receiver might come from this path, that hitting to surface, hitting to bottom, hitting to surface, hitting to bottom, by that way, right? So here we have considered the frequency response of a particular path, kth path, and it is given by the cumulative reflection coefficient tau p divided by, this is the propagation loss, attenuation you can call that. So this attenuation depends on what is your path length, from what path your signal is coming, and what is the absorption by the water itself. So here the overall channel impulse response can be considered as sum of all the impulse responses of multiple paths, right? So I will skip this part. So here, using a model which is presented by Prasarak, who is a well-known researcher in underwater, particularly in seawater. So they have given a model which is called as a Belloff model. So this Belloff model we have utilized. Here we have simulated, we have considered the water depth 25, transmitter height 15 meters, receiver height 15. This is just for a sake of geometry that we have considered. So distance between transmitter receiver, we have taken 100 meters and we have recorded the signal up to 180 seconds. And operating frequency and the bandwidth we considered 10 kilohertz, and the sediment sound speed also is one parameter that we need to consider. So here you can see the time value. Here you can see the delay, at what time the signal arrives, and this P0 indicates for the direct path, then PB indicates bottom reflected path, PS indicates surface reflected path signal, S1, B1. S1 stands for one surface, one bottom. Once again, S1, B1 is there. So you can execute, you can simulate it multiple times. So it is not an ideal environment like we consider for underwater, because of the waves, or pressure in the water. The transmitter and receiver height is going to change, obviously. So the transmitter, in many cases, it might, now we have considered 15 meters, but it won't be 15 meters really. So it can have, it can be at even 10 meters also, or it can be at 13 meters or 17 meters also. So that variation in the transmitter height as well as receiver height we need to consider. So what we did, we allowed this channel geometry to change. We changed the height by plus minus 5 meters for both transmitter and both receiver, and we have calculated, we have captured all these signals, direct path, surface reflected, and all these. So what we did, we tried to fit the PDF, probability density functions. So as the literature suggested that ragging and rice fits well for many of the legs or many of the seeds. But here, what we observed is that we have fitted this PDF for surface reflected path as well as for bottom reflected. Only few two samples I have shown, but we have done it for 100 times, 100 signals. So what we came to a conclusion that we want to know which PDF fits well to my data. So we have done the case goodness of fit test. Many goodness of fit tests are there, but we have selected one parameter, one sample, not one parameter, sorry, one sample test of case goodness of fit. So what we are doing here, we are comparing the distribution of observed data with a specific distribution. Means whether my data follows Weibull distribution, whether my data follows normal distribution or log normal distribution, we have done that. So this D gives us the difference between the theoretical CDF that we have assumed and actual CDF of the data. So these statistics we need to compare, and we have so there is a standard way that you have to compare it with a critical value alpha. So alpha you can take any value. We have taken 0.05. So here you can take that at 0.01 also. It will tell you what is the confidence level with which you are, what is the significance level, sorry, what is the significance level with which you are proving your statement that your data follows a particular distribution, right? So we did this case statistic test, and we observed that whatever is the channel impulse response, it follows a Weibull 3P distribution. 3P stands for 3 parameter. It considers scale, location, and the shape. So Weibull distribution fits to the channel impulse response with a confidence level of 95%. Others fit, but they don't give the optimum performance. But Weibull distribution has given the best performance for the data that we have captured. So the last point of my presentation is talking about what is the sediment type at Khadakwasla Lake. So when we talk about the sediment classification, there are two approaches. One is you can use model-based techniques for sediment classification, or you can use the empirical techniques for sediment classification. When you go with the empirical techniques, you need to have a huge amount of data with you, which has been tagged already. Okay? This is sand, this sample is of sand, this sample is of silt. But getting this sort of data is a very tedious job when you consider a underwater experiment. So what we did, we used the model-based technique, and we have used reflection coefficient and frequency shift model to check what type of sediment is there underwater. So this is the energy model. So transmitted energy, received energy is a function of transmitted energy. R square is a reflection coefficient here. This is alpha, that is absorption coefficient, and height of the that is a water depth. This is water depth. So we know receiver energy, we know the received energy, we know the transmitted energy. We can calculate alpha value based on what is the distance between transmitter and receiver, and from that we can calculate R square. From that we can calculate R. So R is the reflection coefficient. So we have used the standard model, that is a Hamilton model. So Hamilton model will give you the mapping directly. What is the average reflection coefficient and what type of sediment is there. So if you have 0.15 as a reflection coefficient, it goes under silty clay. Then clay is varieties of classes have been mentioned already. So this study we have done. Then another model we have selected, one time domain model we selected and one frequency domain model we have selected for this case study. So we have also selected a relaxation time model. So this relaxation time model talks about rate of change of frequency with along the sediment layer. How is the frequency, instantaneous frequency, to be very specific, how is the change in the instantaneous frequency of the signal as the sound travels inside the sediment? So for that purpose, here this is a sample signal. This we have captured from Khadakwasla Lake. So this is a sample signal of sub-bottom profiler, because we know we now want to know the sediment type. So here along the sediment column, so the transmitted pulse is a Gaussian pulse, that is a chirp signal in the range 2 to 10 kilohertz. The pulse duration was 20 meters and the pulse power was 210 dB. Whatever signal we get from sub-bottom profiler is analytical form. So analytical form means you will have a real part of the signal, you will have an imaginary part of the signal. The imaginary part is itself a Hilbert transform, that is, which will give you the instantaneous frequency of the signal. So the instantaneous frequency here, I will show you that. Just a minute. So see, this is one signal sample I have shown. This is from sub-bottom profiler. So water depth was 10 meters there at a particular location. So from 10 meters to 15 meters, so up to 10 meter, at 10 meters, I got water sediment layer, means first sediment layer. From 10 to 15 meters, you have actual sediment layer. So you can see the behavior of the signal here, that the instantaneous frequency is continuously decreasing. So how is the change of instantaneous frequency over the depth? That is, we have to calculate the slope of this line. So we have once again used here the least square regression model to calculate what is the center frequency shift per meter. And in literature, there is a Leblanc's model. Leblanc's model is there. So this Leblanc's model will tell you what is the relationship between shift in central frequency to the sediment type. Shift in central frequency to the sediment type. So we observed that thus here I have plotted the shift. We have we have done the simulation for on the real data. Obviously, we have done it, worked on the sites S1 to S5 in the Khadakwasla Lake itself. So at various sites, when we observed, the central frequency shift was from 5 hertz per meter to 15 hertz per meter. So it corresponds to relaxation time of 0.02 to 0.0, it's 0.06 microseconds. So this relaxation time corresponds to sediment type, which is clay, fine silt and medium silt respectively. So what we did, central frequency shift, we mapped to relaxation time, and from relaxation time, we have mapped it to the sediment type. So the central frequency shift in the region where we captured the data, it was from 15 to 25 hertz. And in some regions, we found that it was a coarse silt. But if you see the overall, means we have taken the measurements at 6 different sites in Khadakwasla Lake. Wherever we have taken the measurements, we found that the lake was populated with clay, fine and medium silt. So this was the conclusion that we have drawn. Here I have plotted the reflection coefficients. Those reflection, by that way also, we confirmed that the lake was having clay, silty clay and clayey silt as a sediment type. So we have verified by both the methods. So this is a Khadakwasla map, and the star locations you can see that from here we have taken the grabber samples. These are the results that our model has given. But whether really the fact is that whatever we have mentioned here, whether really it is true, at what extent it is true, for that purpose we have collected the ground truth samples. So from these 4 locations we have collected the ground truth samples. I have mentioned the latitude, longitude also. And the samples I will show you, the grabbers we have used, and those grabber samples we have given to Fugro for testing. And the Fugro has given us these laboratory results. I have shown it only for 6 samples. And whatever where our model results, we could really correlate it with the ground truth samples. So this completes my part, but what will be the research and development in this field ahead? As we know, AI has become a buzzword now, machine learning and artificial intelligence. It has also touched to the great extent to underwater acoustic applications. So for marine population detection, for acoustic monitoring, for seafloor mapping, then for underwater surveillance, pipeline and infrastructure inspection, aquatic life monitoring. We can utilize all these for all these applications. We can utilize artificial intelligence and machine learning technique. So what is the challenge? So the challenge, the most important challenge here is the data is not available. When you go for the sea, for the sea, you have a data available. But what location you select, it depends on that. But when you go for the fresh water, no data, literally no data is available in open source domain. So data scarcity is a most important challenge when you go for this working in this field. So when we talk about machine learning, artificial intelligence, we highly require the labeled data, right? So, but when we don't have the labeled data, how we can validate our model? That is a question. And when you decide to collect the data, it is a very costly affair when you want to collect the data. For this 2 days experiment, we have invested round about, I received some funding from BCUD Pune, and my guide also received the funding from Bajaj company. So we have invested more than 5 lakh rupees for collection of the data. So that is one challenge. And but Maritime Research Center is having the data available. Those who are interested, they can approach to Maritime Research Center. Shridhar is working as deputy director there. He can also connect you to Maritime Research Center. And really working in this domain was really a challenge. And but we should accept the challenge and prove that we are right. So the last, as you know, the environmental variability. When you go for these sort of experiments, they are site-specific, seasonal and diurnal variations needs to be taken into consideration. What we can do is, we can have a collaborative approach. We can have the partnership with industries, academia, and we can, when many people are working in this domain, it is also affordable to everyone to collect the funds, attract the funds from government, and plan such big experiments. So even though it is much complex but challenging, but many opportunities are there who want really to work in this domain. Thank you. Thank you.
Thank you, ma'am. Now it's a time of question and answers.
Yes.
All the participants are requested. If you have any question, then you can ask. Both the research persons are there. Sir, I have one question. Is there any limitation in the underwater acoustic communication in terms of the frequencies?
Limitation in underwater acoustic communication in terms of frequencies.
It's to establish communications Like there is any particular band of frequency, or
it depends upon the use case, of course. If we are talking about, as I mentioned, if we are talking about if we want to perform communication over long ranges, then obviously make use of the low frequency. However, if the detail is more important to us, if the information that we need to gather is more important to us, then the high frequency spectrum is much better. In terms of again, so as long as it changes from application to application, as I mentioned, if we are collecting data at a very low depth, we are collecting data at a low distance between the sender and the receiver, then obviously high frequency is good. But yes, that kind of a trade-off is something we need to make. The higher the frequency, the more the attenuation that will happen, and that will create a problem. But in terms of there are like a lot of solutions to overcome these kind of frequency related problems as well. There are a lot of modulation techniques that we can be using. We can use phase shift keying, frequency shift keying, and such kind of things that we can use to overcome frequency related limitations. But more or less, the limitations in underwater acoustics is more due to the external factors of the environment, instead of the frequency as such.
So you can you might have seen that we have worked in 2 to 10 kilohertz, 2 to 12 kilohertz as well. Up to you can work up to 900 kilohertz. Means the maximum limit is you can have up to 1 megahertz. You can utilize those sensors. And
Okay,
as
ma'am.
well as the audio range.
Yes, ma'am, it's fine.
Okay.
From the participant, any question? Okay. Last but not least, the vote of thank. So we are deeply grateful for illuminating this session on underwater acoustic communication. Dr. Jyoti ma'am, you presented in our faculty development program on next generation communication. Your expertise and passion for this subject shown through in your engaging presentation, making complex concepts accessible to our audience. Your valuable insight into latest research and advancement in underwater acoustic communication have broadened our understanding of this critical area. So thank you for generously sharing your time, knowledge, and expertise with us. Your contribution has been invaluable to our FDP. So thank you to both the guests, Mr. Shridhar from Sydney, Australia, and Dr. Jyoti ma'am once again.
Thank you,
Thank you
sir,
very much.
Thank you, sir, for giving us the opportunity. And I'm thankful to Principal Dr. Mukne also for giving us the opportunity to present our work during this FDP. Thank you, sir.
Yes, ma'am. It's our pleasure.
Thank you.
Mukne sir, are you there? You want to express something? Okay. So I think it's fine. So
Okay.
one announcement to all the participants. So there is a day to attendance and feedback link. It is posted in the chat section of Zoom. So hope all of you feel the attendance and feedback. So thank you and good night to all of you. Thank you
sir.
very much.
Good night.
Thank you for your opportunity.
Thank you.